Close your eyes and imagine stepping outside the river of time itself. What if I told you that time travel isn't just science fiction? That astronauts have already done it? That you're doing it right now? That the universe contains natural time machines hidden in the hearts of galaxies? Tonight, we're going on a gentle journey through 100 fascinating facts about time travel. From Einstein's proven theories to mind-bending paradoxes, from black holes that warp reality to the simple truth that your brain experiences time differently than mine. Some of these facts will surprise you. Others might change how you think about yesterday, today, and tomorrow. And a few might make you realize that the impossible is closer than you think. So get comfortable, relax, let your mind wander through the fourth dimension. Fact 1. Einstein proved time travel is real. Let's begin with something truly remarkable. Time travel isn't just science fiction, it's science fact. Albert Einstein changed everything when he published his theory of relativity in the early 1900s. What he discovered was revolutionary. Time isn't the same for everyone, everywhere. It actually moves at different speeds depending on two key factors: how fast you're moving and how much gravity you're experiencing. Think about that for a moment. The clock on your wall and a clock on a speeding spaceship don't tick at the same rate. Time itself stretches and compresses like an elastic fabric. Einstein showed us that time and space are woven together into something called space-time, and this fabric can be bent, warped, and twisted. This means that time travel into the future is not only possible, it's happening all around us, right now. Every single moment, in tiny, imperceptible ways. When you drive your car, you're aging ever so slightly slower than someone standing still. The difference is incredibly small, far too tiny for humans to notice. But it's real, it's measurable, and it's been proven over and over again in laboratories around the world. Einstein's discovery opened a door to possibilities that seemed impossible before. It showed us that our intuitive understanding of time, that steady tick, tick, tick we all experience, is just an illusion. Time is far stranger, far more flexible, and far more wonderful than we ever imagined. Fact 2. Astronauts are technically time travelers. Here's something that might surprise you. Astronauts who travel to space and return to Earth have actually traveled into the future. Not by years or decades, but by tiny fractions of a second. And this has been measured and proven. Consider the Russian cosmonaut Sergei Krikalev. He spent so much time orbiting Earth aboard space stations that he holds a special record. When scientists calculated the time dilation effects of his high-speed orbital journeys, they discovered something amazing. Krikalev had aged about 0.02 seconds less than people who remained on Earth during the same period. Let that sink in for a moment. He literally traveled 0.02 seconds into the future compared to the rest of us. It's a tiny amount, but it's real-time travel. How does this work? When you're orbiting Earth, you're moving at tremendous speeds, around 28,000 kilometers per hour. At these velocities, time moves slightly slower for you compared to people on the ground. This isn't theory or speculation. This is observed, measured, documented reality. Every astronaut who has ever been to space has experienced this. They've all traveled microseconds into the future. They've all lived slightly less time than their twins or friends who stayed on Earth. It's one of the most beautiful confirmations of Einstein's theories. The equations predicted this would happen, and when we finally had the technology to test it, reality matched the mathematics perfectly. Time travel is real, and every astronaut is living proof. Fact 3. GPS satellites must account for time dilation. Every day, billions of people use GPS navigation without realizing they're benefiting from time travel corrections. Yes, your phone's ability to tell you where you are depends on accounting for relativistic time dilation. Without these corrections, GPS would be useless. Here's how it works. GPS satellites orbit Earth at about 20,000 kilometers above the surface. Up there, two different time dilation effects are happening simultaneously. First, the satellites are moving fast, which makes time run slightly slower for them. But second, They're farther from Earth's gravitational field, which makes time run slightly faster for them. These two effects partially cancel each other out, but not completely. The result is that atomic clocks on GPS satellites run about 38 microseconds faster per day than identical clocks on Earth's surface. 38 microseconds might not sound like much, but light travels about 300,000 kilometers per second. In 38 microseconds, signals travel more than 11 kilometers. If GPS systems didn't correct for these relativistic effects, your navigation would be off by several miles after just a few minutes. Within a day, the errors would be enormous, making the system completely useless. Engineers have to program Einstein's equations directly into the GPS system to compensate for time dilation. So every time you use GPS to find a restaurant or navigate to a friend's house, you're using technology that accounts for time travel. It's a hidden reminder that we live in Einstein's universe, where time is relative and flexible. Science fiction has become the invisible foundation of everyday life. Fact 4. Gravity slows time. Imagine two identical clocks, perfectly synchronized. Now place one at sea level and carry the other to the top of a mountain. When you bring them back together, you'll discover something extraordinary. The clock at sea level will show slightly less time has passed. The clock on the mountain will be ahead, even if only by nanoseconds. This happens because gravity warps time itself. The stronger the gravitational field, the slower time moves. At sea level, Earth's gravity is stronger than on a mountaintop, so time runs a little bit slower. This effect is called gravitational time dilation, and it's one of the most fascinating predictions of general relativity. The effect is small on Earth, but it's real and measurable with atomic clocks, which can detect time differences of billionths of a second. Scientists have actually done this experiment, taking atomic clocks to different altitudes and comparing them. The results match Einstein's predictions with stunning accuracy. Now imagine more extreme situations. Near a black hole, where gravity becomes incredibly intense, time slows down dramatically. If you could somehow survive near a black hole's event horizon and then return to Earth, you might find that centuries had passed while only hours passed for you. This isn't speculation. This is how the universe actually works. Gravity doesn't just pull on objects, it pulls on time itself. Every massive object, from planets to stars to galaxies, creates a dip in the fabric of space-time, and at the bottom of these dips, time moves slower. It's beautiful, strange, and absolutely real. Fact 5. The faster you move, the slower time passes. Here's one of the most counterintuitive facts about our universe. The faster you move through space, the slower you move through time. It's not that time seems slower. Time actually is slower for you compared to someone standing still. This is called time dilation, and it's a fundamental feature of reality. At everyday speeds, the effect is impossibly small. When you drive a car at 100 kilometers per hour, you're aging slower than someone standing still. But the difference is so tiny that it would take trillions of years to add up to even 1 second. But as you approach the speed of light, the effects become dramatic. At 90% the speed of light, time runs at about half speed for you compared to a stationary observer. At 99%, it's running at about 1/7 speed. At 99.99%, time almost stops. This has been proven countless times with particle accelerators. Subatomic particles that normally decay in microseconds can be made to last much longer by accelerating them to near light speed. From the particle's perspective, the same amount of time passes. But from our perspective, watching in the laboratory, the particle lives much longer. This is the principle behind many science fiction stories, where astronauts travel to distant stars and return to find Earth centuries older, while they've only aged a few years. It's called the twin paradox, and it's not a paradox at all. It's real physics. The traveling twin really would be younger. The universe allows you to trade speed through space for speed through time. Fact 6. Time dilation has been proven with atomic clocks. In 1971, two physicists named Joseph Haefel and Richard Keating did something extraordinary. They bought tickets on commercial airline flights and took atomic clocks with them. Their goal was to test Einstein's predictions about time dilation in the real world. They flew atomic clocks around the world, first eastward with Earth's rotation, then westward against it. When they returned and compared these traveling clocks with identical clocks that stayed at the United States Naval Observatory, they found exactly what relativity predicted. The eastward flying clocks, which moved faster relative to Earth's center due to the plane's motion plus Earth's rotation, showed less time had passed. They lost about 59 nanoseconds. The westward flying clocks, moving slower relative to Earth's center, gained about 273 nanoseconds. The predictions matched reality within the experimental error margins. This was a landmark moment. Here was direct, undeniable proof that time really does pass at different rates depending on velocity and gravitational field. It wasn't theory anymore. It was measured fact, proven with clocks on passenger jets. Since then, this experiment has been repeated many times with increasingly precise instruments. Every single test confirms the same thing. Time is not absolute. Time is not universal. Time bends and flexes based on motion and gravity. These atomic clock experiments are some of the most important proofs we have that time travel, at least into the future, is real. They show us that the universe is far stranger than our everyday experience suggests, and they open up possibilities that once seemed impossible. Fact 7. Black holes can theoretically allow time travel. Black holes are among the most extreme objects in the universe, and they do extraordinary things to time. Near a black hole, gravity becomes so intense that it warps space-time into bizarre shapes. Time slows down dramatically, and at the event horizon, the point of no return, time from an outside perspective appears to stop completely. If you were watching someone fall into a black hole, you'd see them slow down as they approach the event horizon. They'd appear to freeze, getting dimmer and redder, never quite crossing that boundary. But from the falling person's perspective, time would seem normal, and they'd cross the horizon in finite time. But black holes offer even stranger possibilities. Some black holes rotate, and these are called Kerr black holes. The mathematics of rotating black holes suggests something incredible. Inside them, the extreme warping of space-time might create paths that loop back in time. These are called closed time-like curves. In theory, if you could somehow survive entering a rotating black hole and navigate its interior correctly, you might emerge in the past. The equations suggest this is possible, though the practicalities are overwhelming. The tidal forces would tear apart any known form of matter. And there's the question of whether these mathematical solutions correspond to physical reality. Still, the fact that Einstein's equations allow for these possibilities is profound. Black holes show us that extreme gravity can twist time in ways that permit, at least mathematically, travel to the past. They're natural time machines, written into the fabric of the cosmos itself, waiting at the centers of galaxies throughout the universe. Fact 8. Wormholes are theoretical shortcuts through space-time. Imagine folding a piece of paper so two distant points touch. Now imagine punching through both points to create a tunnel connecting them. That's essentially what a wormhole is, but through the fabric of space-time itself. Wormholes, also called Einstein-Rosen bridges, are solutions to the equations of general relativity. They're theoretical tunnels that could connect distant regions of space and time. You might enter a wormhole on Earth and emerge instantly on the other side of the galaxy. Or you might emerge not just somewhere else, but someone else, in the past or future. The mathematics says wormholes could exist, but there are enormous problems. First, they'd be unstable. They'd collapse almost instantly unless held open by something exotic, matter with negative energy density, which may not exist in nature. Second, even if you could stabilize a wormhole, the tidal forces inside might be lethal. And third, creating one would require manipulating space-time on cosmic scales. Despite these challenges, physicists take wormholes seriously because the equations allow them. Some theoretical models suggest microscopic wormholes might exist at the quantum level, appearing and disappearing in the foam of space-time itself. If traversable wormholes could somehow be created and stabilized, they'd revolutionize everything. Instant travel across the universe. Possible time travel to the past or future. They'd make science fiction scenarios like galactic civilizations actually practical. For now, wormholes remain theoretical, but they remind us that the universe may have hidden structures and shortcuts we haven't discovered yet. Space-time might be far more malleable and strange than we currently understand. Fact 9. The twin paradox is real. The twin paradox is one of the most famous thought experiments in physics, and despite its name, it's not actually a paradox at all. It's a real consequence of special relativity that's been experimentally verified. Here's the scenario. Imagine two twins. One stays on Earth while the other travels in a spaceship to a distant star at near light speed, then returns. When the traveling twin arrives home, they discover something shocking. Their Earthbound twin has aged much more. Decades might have passed on Earth while only a few years passed for the traveler. This seems paradoxical because motion is relative. Shouldn't each twin see the other as the one moving? Shouldn't they both age slower from each other's perspective? But the situation isn't symmetric. The traveling twin accelerates, turns around, and decelerates. They change reference frames. This breaks the symmetry. The mathematics is clear. The twin who travels at high speed really does age slower. This isn't an illusion or a trick. Time genuinely passes more slowly for the traveling twin. When they reunite, the difference in their ages is real and measurable. This has been tested with atomic clocks and particles. Muons, created in Earth's upper atmosphere, travel at near light speed and live longer than they would if they were stationary. The effect is exactly what relativity predicts. So the twin paradox shows us something profound. If we ever develop technology to travel at speeds approaching light speed, the travelers would become time voyagers. They'd be able to journey centuries or millennia into Earth's future while aging only years. One-way time travel to the future is real, proven, and waiting for us to develop the technology. Fact 10. Time moves slower on Jupiter than on Earth. Jupiter, the giant planet in our solar system, has much stronger gravity than Earth. Its mass is about 318 times Earth's mass, and this creates a significantly stronger gravitational field. According to general relativity, this means time runs measurably slower on Jupiter's surface than on Earth. The effect is small but calculable. If you had an atomic clock on Jupiter's surface and an identical clock on Earth's surface, the Jupiter clock would tick slower. Over years and centuries, the difference would accumulate. Someone living on Jupiter would age slightly slower than someone on Earth, all other factors being equal. This isn't just true for Jupiter, it's true for any massive object. Time runs slower at the surface of the Sun than on Earth. Time runs slower on neutron stars, where gravity is millions of times stronger. Near a black hole, time slows down so dramatically that the universe outside appears to fast forward. What makes this particularly fascinating is that it's not a technological limitation or measurement error. It's the actual nature of time itself. If you could somehow establish a video call between Earth and Jupiter with perfect instant communication, you'd see the person on Jupiter moving in slightly slow motion, living life slightly slower. This reveals something deep about the universe. Time isn't a universal constant ticking away the same everywhere. It's a local phenomenon, influenced by mass and energy. Every planet, every star, every particle creates its own temporal environment. The universe doesn't have one clock. It has countless clocks, all running at slightly different rates, creating a tapestry of time flowing at different speeds throughout the cosmos. Fact 11. Every object with mass warps space-time. Right now, as you listen to this, you're warping space-time. It's a tiny effect, almost immeasurably small, but it's real. Every object that has mass, from stars and planets to people and particles, creates a dent in the fabric of space-time. This is the essence of Einstein's general relativity. Think of space-time as a stretched rubber sheet. Place a bowling ball on it and it creates a depression. That's similar to how massive objects warp space-time. Smaller objects, like marbles rolling near the bowling ball, follow curved paths around the depression. That's gravity. Not a force pulling objects together, but objects following the curves of warped space-time. You create a similar effect, though far smaller. Your body's mass creates a tiny dimple in space-time. The effect is so small that it's negligible for all practical purposes. But it exists. Every atom in your body contributes to this warping. This warping affects time as well. At the bottom of a gravitational well, time runs slower. So technically, your feet are aging slightly slower than your head because they're deeper in Earth's gravitational field. The difference is absurdly small, less than nanoseconds over a lifetime, but it's real. This understanding revolutionized physics. It showed that gravity isn't a force transmitted through space, but rather the shape of space itself. Mass tells space-time how to curve, and curved space-time tells matter how to move. It means you're not just moving through space and time. You're part of the fabric itself, constantly influencing it and being influenced by it. You're connected to the cosmic dance of space-time, contributing your small part to the universe's geometry. Fact 12. Muons prove time dilation. Muons are tiny subatomic particles created when cosmic rays strike Earth's upper atmosphere. They're similar to electrons but heavier, and they have a critical property. They're unstable. A muon at rest decays into other particles in about 2 microseconds, 2 millionths of a second. Here's what makes them fascinating for time travel. Muons are created high in the atmosphere, about 15 kilometers up. They travel toward Earth's surface at about 98% the speed of light. At that speed, you'd expect them to travel about 0.6 kilometers before decaying. They shouldn't make it to Earth's surface, but they do. Muons are detected at sea level all the time. This puzzled scientists until they understood time dilation. From our perspective on Earth, the muon is traveling at near light speed, so time passes slower for it. That 2 microsecond lifespan stretches out. The muon lives longer from our perspective, long enough to reach the ground. From the muon's perspective, something equally strange happens. Time passes normally for the muon, but the distance to Earth's surface appears compressed due to length contraction, another relativistic effect. The 15 kilometers shrinks to less than a kilometer, so the muon makes it to the surface in its normal lifetime. Both perspectives are correct. Both describe the same reality from different reference frames. This is relativity in action, happening naturally all around us. Thousands of these tiny time travelers pass through your body every second, living proof that time travel isn't science fiction. Muons have been studied extensively in particle accelerators, and their behavior matches relativity's predictions with extraordinary precision. They're among the most elegant confirmations that time really is relative and flexible. Fact 13. The speed of light is the ultimate speed limit. Light travels at approximately 300,000 kilometers per second in vacuum. This isn't just fast. It's the absolute speed limit of the universe. Nothing with mass can reach this speed, let alone exceed it. This is one of the fundamental laws of physics, baked into the structure of space-time itself. Why is there a limit? It comes from the relationship between energy, mass, and velocity. As an object accelerates closer to light speed, its relativistic mass increases. To go faster requires more energy. As you approach light speed, the energy required approaches infinity. You'd need infinite energy to reach light speed if you have any mass at all. Photons, particles of light, travel at light speed because they have no rest mass. They're born at light speed and always travel at light speed. They never accelerate or decelerate. From a photon's perspective, if it had one, no time passes at all. Its journey from a distant star to your eye is instantaneous from its reference frame. This speed limit has profound implications for time travel. At light speed, time stops completely for you relative to the outside universe. You'd experience no time passing, while the universe around you aged infinitely fast. In a sense, you'd travel instantly to the infinite future. But reaching light speed is impossible for anything with mass. We can only approach it. At 99% light speed, time would slow dramatically, but not stop. The speed of light represents an asymptote. a boundary we can approach but never quite reach. This limit frustrates dreams of easy interstellar travel, but it also protects causality. Without this cosmic speed limit, cause and effect could become scrambled, leading to logical paradoxes that might make the universe inconsistent. Fact 14. Tachyons are hypothetical particles that could travel backward in time. Imagine a particle that moves faster than light, not approaching light speed, but exceeding it. Such particles are called tachyons, and while they're purely hypothetical, their properties are fascinating and strange. The mathematics of relativity, oddly enough, doesn't forbid faster than light particles, but if they exist, they'd have bizarre properties. Tachyons would have imaginary mass, a mathematical property that doesn't correspond to anything we understand physically. They'd also always travel faster than light. They couldn't slow down to light speed, just as normal matter can't accelerate up to light speed. Most intriguingly, tachyons might travel backward in time. As they lose energy, they'd speed up rather than slow down. From certain reference frames, a tachyon moving from point A to point B might appear to be moving from B to A, arriving before it left. If tachyons existed and could be controlled, they'd allow sending information into the past. This opens the door to all sorts of temporal paradoxes. You could theoretically send a message to yourself in the past, which raises questions about causality and free will. Despite decades of searching, no evidence of tachyons has ever been found. Most physicists believe they don't exist. They might be mathematical artifacts, solutions to equations that don't correspond to physical reality. The universe might have mechanisms that prevent faster-than-light particles from existing. Still, the tachyon concept shows us how deeply strange physics becomes when we push it to extremes. It reminds us that the universe might have hidden layers of reality we haven't discovered, and that time might be even more flexible than we currently understand. Fact 15. Closed time-like curves are mathematical solutions in relativity. In the mathematical framework of general relativity, there exist solutions called closed time-like curves, or CTCs. These are paths through space-time that loop back on themselves. If you followed one, you'd return to the same point in space and time where you started. You'd meet yourself in the past. These aren't just theoretical fantasies. They're legitimate solutions to Einstein's field equations under certain conditions. Some rotating black holes might contain CTCs in their interiors. Certain configurations of cosmic strings, hypothetical defects in space-time, might create them. Even some models of the universe itself, like Gödel's rotating universe, contain CTCs. The existence of these solutions raises profound questions. Do they represent physical reality, or are they mathematical curiosities that can't actually occur in nature? Most physicists suspect the latter. There might be unknown principles, sometimes called chronology protection, that prevent closed time-like curves from forming. If CTCs could exist and be traversed, they'd enable genuine time travel to the past. You could loop back and witness, or even interact with earlier events. This opens the door to paradoxes like the grandfather paradox, where you might prevent your own existence. Some theories suggest that if you tried to change the past while traveling through a closed time-like curve, quantum mechanics or other effects would conspire to prevent paradoxes. Everything would happen in a self-consistent way. Your attempts to change history would fail, or you'd discover you were always part of history to begin with. Closed time-like curves represent one of the deepest mysteries in physics, where general relativity, quantum mechanics, and causality all collide in fascinating ways. Fact 16. The grandfather paradox. The grandfather paradox is perhaps the most famous time travel paradox. It's simple to state, but profound in its implications. Imagine you travel back in time and accidentally or intentionally prevent your grandfather from meeting your grandmother. Your parent is never born. You're never born. But if you're never born, you can't travel back in time. So your grandfather does meet your grandmother. So you are born. So you can travel back. And round it goes. This paradox reveals a fundamental tension between time travel to the past and causality. If the past can be changed, cause and effect break down. Effects could erase their own causes. The logical structure of reality seems to collapse. Physicists and philosophers have proposed many solutions. One is the self-consistency principle. Perhaps the universe only allows self-consistent timelines. If you travel to the past, you were always part of that past. You can't change history because your actions were already part of history. You might try to stop your grandparents from meeting, but somehow you'd fail. Another solution is the many worlds interpretation. When you travel to the past and change something, you branch off a new timeline, a parallel universe. In that timeline, you're never born. But in your original timeline, everything remains unchanged. There's no paradox because you're not erasing yourself from your own timeline, just creating a new one. A third possibility is that time travel to the past is simply impossible. The universe might have laws we don't yet understand that prevent closed causal loops and paradoxes from forming. The grandfather paradox isn't just about time travel, it's about the nature of causality, free will, and the consistency of reality itself. Fact 17. The bootstrap paradox. The bootstrap paradox, also called an ontological paradox or causal loop, involves objects or information that exist without ever being created. Imagine this scenario. You love a particular book. You travel back in time and give it to the author before they write it. The author publishes it. Years later, you buy it and eventually travel back to give it to the author. Where did the book come from? Who actually wrote it? The information in the book exists in a closed causal loop. It has no origin point. It wasn't created. It simply exists, passed from future to future again. This violates our intuitive understanding of causation, where everything has a source. Bootstrap paradoxes can involve physical objects, information, or even people. Imagine someone who only exists because they traveled to the past and arranged their parents' meeting. They caused their own existence. But how could they exist to do that in the first place? These paradoxes are particularly troubling because they seem to violate not just causality, but also conservation principles. The information or matter in a bootstrap loop appears from nowhere. There's no moment of creation, no input of energy or creativity. Some physicists argue that if time travel to the past is possible, bootstrap paradoxes might be inevitable and not actually problematic. The universe might simply contain these self-sustaining causal loops. Others see them as evidence that backward time travel is impossible. The bootstrap paradox highlights a deep question. Does the universe require that everything has a beginning? Or could there be things that exist without origin, sustained by temporal loops? It challenges our deepest assumptions about causation and existence. Fact 18. The predestination paradox. The predestination paradox occurs when actions taken to prevent an event actually cause that event. You try to change the future, but your efforts ensure the future happens exactly as you foresaw. It's a frustrating situation where free will seems to vanish and fate becomes inescapable. A classic example comes from Greek mythology. King Laius receives a prophecy that his son will kill him. To prevent this, he abandons the infant Oedipus, but this abandonment sets in motion events that lead to Oedipus unknowingly killing his father years later. The attempt to avoid destiny fulfilled it. In time travel contexts, imagine learning about a disaster and traveling to the past to prevent it. But your presence in the past, your warnings or actions, turn out to be the very cause of the disaster. The time loop closes. Your knowledge of the future and attempt to change it guarantee it happens. This paradox raises questions about determinism and free will. If the future is fixed and knowable, do our choices matter? Or is the appearance of choice itself an illusion, with our actions predetermined by the necessity of maintaining timeline consistency? Some interpretations of time travel suggest that predestination paradoxes prove the universe is self-consistent. You can't change history because your actions were always part of history. The timeline includes all your attempts to alter it. You're playing a role in a story that's already written, even from your perspective in the past. Others see predestination paradoxes as evidence that foreknowledge is impossible or that multiple timelines exist. Perhaps every choice creates a new branch, and predestination only applies within single branches. Fact 19. The Novikov self-consistency principle. Physicist Igor Novikov proposed an elegant solution to time travel paradoxes, the self-consistency principle. It states simply that if time travel is possible, only self-consistent timelines can exist. Events must form consistent loops. Paradoxes are impossible not because time travel is impossible, but because inconsistent histories can't happen. Under this principle, if you travel to the past, you were always there. History is immutable, not because it's fixed independently, but because any changes you make were always part of that history. You can't kill your grandfather because you didn't. You can't change the outcome of a historical event because you didn't. The timeline is self-enforcing. This might work through quantum mechanics. Perhaps at the quantum level, only self-consistent histories have non-zero probability. Inconsistent timelines have zero probability of occurring. Nature selects for consistency automatically. Alternatively, perhaps something would always prevent you from creating a paradox. If you try to kill your grandfather, your gun jams. You slip and miss. He survives unexpectedly. Every attempt fails through apparent coincidence, but really through cosmic necessity. The Novikov principle is appealing because it allows time travel without paradoxes. It suggests a universe that's logically coherent and self-consistent, but it raises uncomfortable questions about free will. If your actions in the past are constrained by the necessity of maintaining consistency with the already existing future, are you truly free? Some physicists embrace this view. Others find it unsatisfying, arguing it seems contrived or that it smuggles in hidden assumptions. The debate continues, touching deep issues about the nature of time, causality, and possibility. Fact 20. Multiple timeline theory. One of the most popular solutions to time travel paradoxes is the multiple timeline or many worlds theory. When you travel to the past and change something, you don't alter your original timeline. Instead, you create a new parallel universe that branches off from the moment you arrive. In this framework, the grandfather paradox dissolves. You travel to the past and prevent your grandparents from meeting. In the new timeline that results, you're never born. But that's fine because you came from a different timeline where you were born. Your existence isn't threatened because your original timeline remains unchanged. This idea connects to the many worlds interpretation of quantum mechanics, which suggests that every quantum measurement causes reality to split into multiple branches, each representing different outcomes. Time travel might work similarly, with each change in the past creating a new branch. The advantage of this theory is that it preserves causality within each timeline while allowing freedom across timelines. You can change history, just not your own history. You can save Lincoln or prevent wars, but you're saving Lincoln in an alternate timeline, creating a new universe where things went differently. The downside is proliferation. If every time travel event creates new timelines, and if time travel becomes common, the universe would fracture into an incomprehensibly vast number of parallel worlds. There'd be timelines where every possible variation of events occurred. Multiple timeline theory also raises philosophical questions. If you save someone in an alternate timeline, have you really saved them? The version in your original timeline remains dead. Have you done something meaningful, or just created an alternative where someone else is alive? Fact 21. The butterfly effect. The butterfly effect, coined by mathematician Edward Lorenz, suggests that tiny changes can have enormous consequences. A butterfly flapping its wings in Brazil might set off a chain of atmospheric changes that eventually cause a tornado in Texas. Small differences in initial conditions lead to vastly different outcomes. This concept has profound implications for time travel. If you go to the past and change even the tiniest thing, step on an insect, move a pebble, breathe differently, the cascade of consequences might radically alter the future. By the time you return to your present, everything might be unrecognizably different. This isn't just theoretical concern. Chaos theory shows us that many systems are extremely sensitive to initial conditions. Weather, ecosystems, even human history might be chaotic in this technical sense. Deterministic, but unpredictable, with small changes amplifying over time. Ray Bradbury explored this in his short story, A Sound of Thunder, where a time traveler accidentally steps on a butterfly in the prehistoric past and returns to find his present radically changed. It's become the classic cautionary tale about time travel. The butterfly effect suggests that even if time travel were possible, it would be incredibly dangerous. You couldn't just visit the past as a passive observer. Your mere presence would change things. Photons from your body would interact with the environment. Your gravity would minutely affect nearby objects. These tiny perturbations could snowball. This might be another form of chronology protection. Perhaps the universe prevents time travel precisely because it would be too destabilizing. Or perhaps the butterfly effect ensures that history remains roughly the same despite minor interference, with small changes washing out over time rather than amplifying. Fact 22. Causal loops are events that cause themselves. A causal loop is an event or object that exists within a closed chain of causation, where the event is among the causes of itself. These loops seem to violate our understanding that causes must precede effects and that infinite regress is impossible. Yet they appear naturally in some time travel scenarios. Imagine this. You receive detailed plans for a time machine from your future self. You build it using those plans. Years later, you travel back and give those same plans to your younger self. The plans exist in a perfect loop. They were never invented. They simply cycle through time. Or consider a person whose existence depends on their own time travel. They go back and save someone's life. That someone turns out to be their own grandparent. Without the time travel, the grandparent dies and the time traveler is never born. But their existence enables the time travel that ensures their existence. Causal loops challenge the principle of sufficient reason, the idea that everything must have an explanation outside itself. In a causal loop, things explain themselves through temporal circularity. The loop as a whole has no external cause. Some physicists argue these loops are perfectly consistent with the laws of physics, just strange to our intuition. Others see them as evidence that backward time travel might be impossible, or that additional principles govern time travel that we haven't discovered yet. Causal loops also appear in quantum mechanics and cosmology. Some interpretations of quantum measurement involve retrocausal effects, where measurements affect the past, and some cosmological models suggest the universe itself might be in a causal loop, with the Big Bang somehow caused by the universe's own future. These loops reveal that time might not be the simple linear flow we experience. Causation might be more circular, more interconnected. Causes and effects might form webs rather than chains, with future events reaching back to influence their own origins in ways that seem paradoxical but might be perfectly natural. Fact 23. The information paradox. The information paradox in time travel concerns a fundamental question. Where does information come from? In a bootstrap paradox, information exists in a closed loop with no origin point. This seems to violate basic principles about how knowledge is created. Imagine you travel forward in time and learn the solution to a famous mathematical problem. You bring this solution back to the present and publish it. The mathematical world celebrates. But where did the solution actually come from? Who did the creative work of discovering it? In the future, people know it because you published it, but you published it because you learned it in the future. The information seems to have emerged from nowhere, violating what we might call conservation of information or creativity. Normally, information is created through observation, deduction, or creative insight. Someone does the work, but in temporal loops, the work seems to vanish. The information perpetuates itself without ever being generated. This is particularly troubling in quantum mechanics, where information conservation is a fundamental principle. Quantum information can't be created or destroyed, only transformed. Bootstrap paradoxes seem to violate this. Information appears to exist outside the normal flow of cause and effect. Some physicists propose that if time travel is possible, information in loops must be self-consistent in ways we don't yet understand. Perhaps quantum mechanics provides hidden mechanisms that ensure consistency. Or perhaps the information in a loop isn't truly created from nothing, but exists in a superposition of states that collapse into consistency. Others see the information paradox as strong evidence against backward time travel. If time travel creates logical impossibilities around information, perhaps nature prevents it. The paradox itself acts as a barrier, making closed time-like curves impossible to traverse. Fact 24. Temporal paradoxes could violate conservation of energy. Conservation of energy is one of the most fundamental principles in physics. Energy cannot be created or destroyed, only transformed. But time travel paradoxes seem to threaten this law. Consider what happens if you bring matter from the future to the past. Imagine you travel to the future and pick up a gold brick. You bring it back to the present. Now, there are two versions of that gold brick existing simultaneously. The one you brought back, and the one that will eventually become the brick you picked up. Where did the energy come from to create the duplicate? Or consider a causal loop with a physical object. You receive a watch from your future self, wear it for years, then travel back and give it to your younger self. That watch exists in an endless cycle, never manufactured, never destroyed. It seems to violate thermodynamics. It should wear out, accumulate entropy, but instead it loops perfectly unchanged. The energy and matter in temporal loops appear from nowhere, violating conservation laws. This is one of the most serious objections to time travel. Physics cannot permit violations of energy conservation without undermining the entire theoretical framework. Possible resolutions include multiple timelines, where energy is conserved within each timeline separately. Or perhaps, quantum mechanics ensures conservation in ways we don't understand, with virtual particles or other effects balancing the books. Some theories propose that creating a time machine or traversing a closed time-like curve requires exactly the right amount of energy to balance what appears in the past. The energy paradox suggests that if time travel is possible, it must work in ways that preserve fundamental conservation laws. The universe must have hidden mechanisms to maintain consistency. Fact 25. The ontological paradox. The ontological paradox asks a deceptively simple question. Can something exist without being created? In philosophy, ontology is the study of existence and being. An ontological paradox involves something that exists but has no origin point in time. We've touched on this with bootstrap paradoxes, but it's worth exploring more deeply. Consider not just objects or information, but existence itself. Imagine a person who only exists because they time traveled and caused their own birth. They create themselves. But how could they exist to do the creating before they were created? This strikes at the heart of our understanding of causation and existence. We normally think everything that exists must have come into being at some point. There must be a first cause, an origin. But temporal loops suggest otherwise. They suggest existence without beginning, being without becoming. Some philosophers argue this is logically impossible. Existence requires a temporal starting point. Others suggest it's only impossible given our limited understanding of time. If time is circular, or if multiple timelines exist, perhaps existence without origin makes sense. The ontological paradox also connects to questions about the origin of the universe itself. If time began with the Big Bang, what caused the Big Bang? Some cosmological models suggest the universe might be in a causal loop with itself, existing without external cause. Time and existence might form a self-sustaining system. In a way, ontological paradoxes challenge the deepest assumption we have, that reality must have a foundation, a ground, an ultimate explanation. They raise the possibility that existence might be fundamentally circular, self-referential, without ultimate origin or explanation. Fact 26. Free will becomes questionable if the future is fixed. Time travel raises profound questions about free will. If the future already exists in some sense, and if time travel to the past is possible, then it seems the future must be fixed. Every choice you make was already determined by the fact that the future already happened. Your sense of free choice might be an illusion. Consider a simple scenario. You travel to the future and witness a specific event. Then you return to the present. Can you prevent that event now that you know it will happen? If you can prevent it, then what you witnessed wasn't the real future. But if you can't prevent it, then your choices are determined. You're destined to act in ways that ensure the future you witnessed comes to pass. This is deeply unsettling. We experience ourselves as free agents making genuine choices. But if the future exists as definitely as the past, then all our choices are already made. The book of history is written, and we're simply reading it page by page, with the illusion of writing it as we go. Some philosophers argue that free will and a fixed future are compatible. Perhaps free will means doing what you want without external constraint, even if what you want is determined by prior causes. Your choices are still yours, even if they're inevitable. Others embrace the view that time travel proves determinism. Everything that happens must happen. The universe is a four-dimensional block where past, present, and future all exist eternally, and free will is indeed an illusion. Still others reject the premise, arguing that the future doesn't exist until it happens, that time travel to the past might be impossible, or that multiple timelines preserve free will by allowing different choices in different branches. Fact 27. The many worlds. Interpretation might solve paradoxes. The many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957, suggests something extraordinary. Every time a quantum event could go multiple ways, reality splits. All outcomes occur, each in a separate parallel universe. Reality is constantly branching into countless parallel worlds. This interpretation offers an elegant solution to time travel paradoxes. When you travel to the past and change something, you don't alter your original timeline. You create a branch point. From that moment, the timeline splits. In one branch, events proceed as they originally did. In another, they proceed with your changes. You can prevent your own birth in the new timeline without paradox, because you originated from a different timeline where you were born. You can kill Hitler, save Lincoln, or prevent disasters, but you're doing so in newly created parallel universes, not your own history. This preserves causality while allowing freedom. Every possible action you take creates a new world. The multiverse contains all possible histories, all possible futures. Time travelers are world creators, not history changers. The many worlds interpretation is controversial. It seems extravagant, multiplying universes without limit. But it solves the measurement problem in quantum mechanics and time travel paradoxes with the same elegant mechanism. Some physicists take it very seriously. If it's correct, then time travel becomes exploration of the multiverse rather than rewriting history. You can't save your own world's past, but you can create better alternative worlds. Every time travel journey is a one-way trip to a new branch of reality, forever separated from your origin. Fact 28. Chronology protection conjecture. Physicist Stephen Hawking proposed the chronology protection conjecture. The universe protects itself from time travel paradoxes. Nature abhors a time machine. Whenever conditions arise that might permit backward time travel, physics conspires to prevent it. Hawking suggested that quantum effects might destroy any time machine just as it's about to form. As space-time curves enough to create closed time-like curves, quantum fluctuations would grow without bound, creating infinite energy densities that tear apart the time machine. This is nature's way of protecting causality. The laws of physics might have built-in safeguards that prevent paradoxes by preventing the conditions that would create them. It's a cosmic censorship, but for time rather than black hole singularities. Evidence for chronology protection is circumstantial. We've never observed closed time-like curves or time machines. Whenever physicists devise theoretical time machines, they require exotic conditions: negative energy, infinitely long rotating cylinders, manipulated wormholes. These might be precisely the things nature forbids. But chronology protection remains a conjecture, not proven law. We don't know if it's right. Maybe time travel is possible, and paradoxes resolve through other means. Maybe closed time-like curves exist, but can't be traversed. Or maybe we simply haven't discovered how to build time machines yet. The conjecture reflects a deep intuition that the universe must be logically consistent. If backward time travel creates insoluble paradoxes, then it should be impossible. Nature should have mechanisms, perhaps quantum mechanical, that maintain order and causality. But this remains speculative, a hint of deeper principles we haven't yet uncovered. Fact 29. Quantum mechanics might allow small-scale time travel, while relativity governs large-scale space-time. Quantum mechanics rules the subatomic world, and in that strange quantum realm, time behaves even more mysteriously than in relativistic physics. Some interpretations of quantum mechanics allow for retrocausal effects, where future events influence the past. The delayed choice quantum eraser experiment suggests that measurements made in the future can affect the behavior of particles in the past. A photon's path seems to be determined retroactively based on later measurements. It's as if the future reaches back to influence the past at quantum scales. This doesn't allow sending messages or macroscopic objects backward in time. The effects are subtle, observable only in carefully controlled quantum experiments. But they suggest that at the quantum level, time's arrow isn't as rigid as we thought. Some physicists propose that microscopic closed time-like curves might exist in the quantum foam of spacetime. At the Planck scale, smaller than anything we can observe, spacetime might be roiling with tiny wormholes and temporal loops that appear and disappear constantly. These quantum time travel effects wouldn't enable the sort of time travel we imagine in science fiction. You couldn't send your consciousness back or visit ancient Egypt, but they suggest that nature might permit limited forms of backward causation on small scales, even while preventing larger paradoxes. Understanding quantum time travel effects might eventually reveal new principles that unify quantum mechanics and general relativity. The intersection of these theories, particularly around black holes and the Big Bang, remains one of physics' deepest mysteries. Fact 30. The arrow of time points forward. Due to entropy, time has a direction. We remember the past but not the future. Eggs break but don't unbreak. Heat flows from hot to cold but not vice versa. This directional flow is called the arrow of time, and it's deeply connected to entropy, the measure of disorder. The second law of thermodynamics states that entropy, disorder, always increases in closed systems. This law gives time its arrow. When you see a video of an egg unbreaking, you know it's running backward because it violates the entropy increase we expect. But here's something fascinating. The fundamental laws of physics, from Newtonian mechanics to relativity to quantum mechanics, are time symmetric. They work equally well forward or backward in time. An electron moving forward in time is mathematically equivalent to a positron moving backward. At the deepest level, physics doesn't care about time's direction. The arrow of time emerges from statistics and initial conditions. The universe started in an extremely low entropy state at the Big Bang. Since then, entropy has been increasing, creating the arrow we experience. The future is the direction of increasing disorder. This means the arrow of time isn't fundamental. It's emergent, arising from the universe's particular history and boundary conditions. In principle, in a universe that began with high entropy or in local regions where entropy decreases, time might flow backward. Some speculate that if time travel to the past is possible, travelers might experience reversed entropy. Ice cubes would spontaneously warm water. Broken eggs would reassemble, but this seems unlikely. More probable is that entropy would continue increasing along the traveler's subjective time, even if they're moving backward through external time. Fact 31. Rotating black holes might allow passage. Without hitting the singularity, most black holes rotate, often at tremendous speeds. These are called Kerr black holes, named after physicist Roy Kerr, who solved Einstein's equations for rotating black holes. Their properties are even stranger than non-rotating black holes. A rotating black hole has two event horizons and a ring singularity rather than a point singularity. Between these horizons is a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Here, standing still becomes impossible. You're forced to move with the rotation. The mathematics of Kerr black holes suggests something remarkable. If you could somehow survive the journey, entering precisely the right way and navigating the interior correctly, you might pass through the ring singularity without being destroyed. On the other side, some solutions suggest you'd emerge in a different region of space-time. Depending on the black hole's properties and your trajectory, you might exit in a different location in space, a different time, or even a different universe. The black hole becomes a gateway, a passage to elsewhere and elsewhen. This is all theoretical. The tidal forces near a black hole would tear apart any known form of matter. The radiation environment would be lethal, and we're not certain the mathematical solutions correspond to physical reality. Quantum effects might change everything at the singularity, but the possibility is tantalizing. Nature might have created tunnels through space-time at the hearts of galaxies. These cosmic maelstroms might be more than dead ends. They might be doorways, if only we could survive to use them. Rotating black holes represent one of the universe's deepest mysteries and most exotic possibilities. Fact 32. The Tipler cylinder is a theoretical time machine. In 1974, physicist Frank Tipler proposed a theoretical time machine, an infinitely long cylinder of incredibly dense matter rotating at near light speed. The cylinder's rotation would drag space-time around it so severely that closed time-like curves would form nearby. If you traveled in a spacecraft spiraling around this Tipler cylinder, following the right trajectory, you'd loop back to your own past. You'd arrive before you left. The cylinder wouldn't be a portal to enter, but rather a region of warped space-time to navigate around. The requirements are extreme. The cylinder must be infinitely long, or at least extremely long. It must rotate at a significant fraction of light speed, and it must be extraordinarily dense, containing about the mass of the Sun, compressed into a volume the size of a small mountain stretched across its length. Constructing such an object is far beyond any imaginable technology. It would require manipulating stellar masses, achieving impossible rotational speeds, and somehow creating an infinite or near-infinite structure. For all practical purposes, it's impossible. But what makes the Tipler cylinder important is that it's a solution to Einstein's equations. It proves that general relativity allows time machines, at least in principle. The laws of physics as we understand them don't forbid such structures. Whether they could actually exist is another question. Perhaps quantum mechanics or other principles unknown to us prevent their formation. Perhaps the infinite length requirement is a hint that they're not physically realizable. But the Tipler cylinder shows us that space-time is malleable enough to permit time travel if we could only warp it correctly. Fact 33. Alcubierre drive could theoretically enable faster-than-light travel. In 1994, physicist Miguel Alcubierre proposed a method for faster-than-light travel that doesn't violate relativity. The idea is elegant. Instead of moving through space, you warp space itself, contracting it in front of you and expanding it behind you, surfing on a wave of space-time. Inside the Alcubierre bubble, you remain stationary in your local reference frame. You don't experience time dilation or relativistic effects. But the bubble itself moves through space faster than light. From an outside perspective, you're crossing vast distances almost instantly. This doesn't violate relativity because you're not moving faster than light through space. Space itself is moving. Einstein's speed limit applies to motion through space, not to the expansion or contraction of space itself. The universe's expansion after the Big Bang moved distant galaxies away from us faster than light, and that's perfectly fine. The catch, and it's enormous, is that the Alcubierre drive requires negative energy density. You need exotic matter that has negative mass, which may not exist. The energy requirements are also astronomical, possibly requiring more energy than exists in the entire universe. There are also questions about causality. If you could travel faster than light in any reference frame, even by warping space, you might be able to arrange your journey to arrive before you left from another perspective, creating time travel and paradoxes. Still, the Alcubierre drive is a legitimate solution to Einstein's equations. It shows that faster than light travel might not be absolutely forbidden, just incredibly difficult. It keeps the dream alive that someday, with enough knowledge and technology, we might slip the bonds of light speed. Fact 34. Cosmic strings are hypothetical defects in space-time. Cosmic strings are theoretical defects in the fabric of space-time itself, left over from the early universe. Imagine a crack frozen into ice as water freezes. Similarly, as the universe cooled after the Big Bang, imperfections might have frozen into space-time structure. These strings would be incredibly thin, possibly thinner than a proton, but immensely long, stretching across light years or more. Despite their thinness, they'd be stupendously dense, with a single kilometer of cosmic string possibly weighing more than Earth. The intense gravity of cosmic strings would severely warp space-time around them. Some theoretical models suggest that if two cosmic strings passed by each other at high speed, or if a single string formed a loop, closed time-like curves might form in their vicinity. Space travelers navigating near these strings might be able to loop back to their own past. The energy and warping effects of cosmic strings could also potentially be harnessed to create wormholes or other exotic space-time structures. They'd be like cosmic infrastructure left by the universe's formation, waiting to be discovered and utilized. However, despite extensive searches, no cosmic strings have ever been observed. They remain purely hypothetical. They might not exist, or they might be so rare that we haven't encountered one yet. The universe might not have produced them during its formation, but the possibility remains tantalizing. Cosmic strings represent another way the universe might naturally create conditions for time travel. They'd be defects in reality itself, scars from the Big Bang, offering shortcuts and strange loops through space-time for civilizations advanced enough to find and use them. Fact 35. Traversable wormholes would require exotic matter. Wormholes are shortcuts through space-time, tunnels connecting distant points. But there's a serious problem with making them traversable. According to general relativity, wormholes tend to collapse almost instantly. To keep one open long enough for anything to pass through, you'd need something extraordinary, exotic matter with negative energy density. Normal matter has positive energy. Even antimatter has positive energy. Negative energy seems to violate every intuition, but quantum mechanics suggests it might be possible in limited amounts. The Casimir effect, where two metal plates in vacuum attract each other, demonstrates something like negative energy on tiny scales. For a traversable wormhole, you'd need enormous amounts of negative energy, arranged in a precise configuration to hold the wormhole's throat open. The requirements might be impossible. Current physics doesn't offer any way to collect and manipulate negative energy on macroscopic scales. There's also the question of stability. Even if you could create a wormhole with exotic matter, would it remain stable? Would quantum fluctuations or passing matter destabilize it? Would it collapse if you tried to send something through? Some theoretical models suggest that advanced civilizations might manipulate black holes, exotic matter, or other structures to create and maintain wormholes. It would require energy and technology far beyond anything we can imagine. But it might not be absolutely forbidden by physics. Traversable wormholes represent perhaps the most practical route to time travel, if they're possible at all. A wormhole could connect not just different places, but different times. Enter one end now, exit the other yesterday. But the challenges are immense, possibly insurmountable. Nature guards its secrets jealously. Fact 36. Quantum entanglement shows instant connections. Quantum entanglement is one of the strangest phenomena in physics. Two particles can become entangled, connected in such a way that measuring one instantly affects the other, no matter how far apart they are. Change the spin of one entangled particle, and its partner, light years away, changes instantly. Einstein called this spooky action at a distance, and was deeply uncomfortable with it. It seems to violate relativity's speed limit. information appears to travel faster than light. But experiments have confirmed entanglement is real. The connection is instant, happening without any signal traveling through space. This raises an obvious question. Could entanglement be used for time travel or faster than light communication? Unfortunately, no. While the correlation between entangled particles is instant, you can't use it to send information. The outcomes of quantum measurements are random. You can't control what result you'll get, so you can't encode a message. When you measure one entangled particle, its partner's state changes instantly, but in a random way consistent with quantum probability. Only by comparing your results with your partner's through normal, slower than light communication can you see the correlation. The entanglement doesn't allow sending information backward in time or faster than light. Some physicists speculate that entanglement might hint at deeper structures in space-time. Perhaps entangled particles remain connected through microscopic wormholes. Perhaps quantum mechanics and relativity meet in ways we don't yet understand, with entanglement revealing hidden connections between distant points in space and time. Entanglement shows us that the universe is far more interconnected than classical physics suggested. But it guards causality carefully. You can't exploit these strange connections to violate the cosmic speed limit or send messages to your past. Fact 37. Frame dragging occurs. When massive rotating objects twist, space-time frame dragging, also called the Lense-Thirring effect, is a prediction of general relativity that's both subtle and profound. When a massive object rotates, it drags space-time around with it, like honey slowly swirling around a spinning spoon. Earth rotates, so it drags space-time around itself slightly. The effect is tiny but measurable. The Gravity Probe B satellite mission, launched in 2004, measured this frame, dragging with incredible precision, confirming Einstein's predictions. Near more massive, faster rotating objects, frame dragging becomes dramatic. Close to a rotating black hole, frame dragging is so intense that nothing can remain stationary. Everything is forced to rotate, along with the black hole's spin. This region is called the ergosphere. Frame dragging connects to time travel because it's another way rotation affects space-time structure. Combined with other effects, extreme frame dragging might contribute to the formation of closed time-like curves. In some theoretical models, rapidly rotating dense objects create time travel possibilities. The phenomenon also demonstrates how intimately motion and space-time are connected. Matter doesn't just sit in space-time like objects in a container. Matter and space-time interact continuously, influencing each other. Mass warps space-time, and moving mass stirs it, creating currents and eddies in the fabric of reality. Frame dragging is subtle evidence that space-time is dynamic, responsive, and far stranger than empty stage where events occur. It's an active participant in cosmic dynamics, twisted and shaped by every massive object, especially those spinning at high speeds. Understanding frame dragging deepens our comprehension of how gravity and motion interweave. Fact 38. The Deutsch-Politzer time machine uses quantum mechanics. Physicist David Deutsch proposed a model of time travel based on quantum mechanics that avoids paradoxes through a clever mechanism. In the Deutsch-Politzer time machine, quantum effects prevent inconsistent histories from occurring. The idea uses the many worlds interpretation. When you attempt time travel that would create a paradox, quantum mechanics automatically selects a self-consistent timeline. If you try to kill your grandfather, quantum effects ensure you fail. Not through chance or coincidence, but through the fundamental, probabilistic nature of quantum mechanics. In this model, closed time-like curves don't allow true freedom to change the past. They constrain your actions through quantum mechanical necessity. The past becomes a boundary condition that determines what quantum states are possible. Only self-consistent loops can actually occur. This preserves both time travel and causality. You can visit the past, but you can't create paradoxes because nature won't allow the quantum states that would lead to paradoxes. The probabilities work out such that every attempted paradox fails. Critics argue this seems like a way to save time travel by gutting its interesting possibilities. If you can't change anything significant, What's the point? But defenders say it's more subtle. You can do things in the past, just not things that would create logical contradictions. There's a space of possible actions, constrained by consistency requirements. The Deutsch-Politzer approach shows how quantum mechanics might police time travel using indeterminacy and superposition to enforce consistency. It suggests that if nature allows closed time-like curves, it has built-in mechanisms to prevent the paradoxes they might otherwise create. Fact 39. Gödel's rotating universe was a solution allowing time travel. Kurt Gödel, famous for his incompleteness theorems in mathematics, also made a surprising contribution to physics. In 1949, he found an exact solution to Einstein's field equations, a rotating universe that allows time travel. In Gödel's universe, space-time has a global rotation. There's no center to this rotation. The entire universe spins. In such a universe, closed time-like curves exist. By traveling along certain paths, you could return to your own past. Gödel's solution shocked physicists, including Einstein himself. It showed that general relativity, in principle, permits time travel. The equations don't forbid it. Under the right cosmic conditions, visiting the past is possible. However, observations show our actual universe isn't rotating in the way Gödel's solution requires. Our universe expands, but doesn't spin globally. Gödel's universe remains a mathematical curiosity rather than a description of reality. Still, it was profoundly important historically. It demonstrated that time travel isn't automatically impossible in relativity. It raised deep questions about the nature of time. If some solutions to Einstein's equations allow time travel, what principle separates physical solutions from mere mathematical possibilities? Gödel's work also illustrated the close relationship between cosmology and time. The global structure of the universe, its overall geometry and dynamics, determines whether time travel is possible. Time isn't just a local phenomenon, but is tied to the universe's largest scale structure. Gödel's rotating universe remains a fascinating footnote in physics history, a reminder that the universe might have been stranger than it is, and that our understanding of time depends on understanding the cosmos as a whole. Fact 40. Retrograde. Time travel, moving backward, might require infinite energy. Moving forward through time is easy. You're doing it right now. Even accelerating your forward motion through time by moving at high speeds to experience less time than stationary observers requires finite, though possibly enormous, energy. But moving backward might be infinitely harder, perhaps impossible. The problem is that traveling backward in time seems to require conditions that become more extreme without limit. You'd need to exceed the speed of light, which requires infinite energy. Or you'd need to create and traverse a wormhole, which might require infinite negative energy. Or you'd need to manipulate space-time in ways that demand more energy than exists. Every theoretical time machine proposed, from tipless cylinders to traversable wormholes, requires either infinite resources or exotic conditions that might not be possible. It's as if nature erected an infinite barrier to protect the past from interference. This might be a clue that backward time travel is truly impossible, not just difficult. Perhaps the energy requirements are a hint that physics fundamentally forbids it. Or perhaps we haven't discovered the clever trick that makes it possible with finite energy. Some speculations suggest that quantum mechanics might allow microscopic backward time travel without infinite energy, that particles might slip through space-time in ways macroscopic objects can't. Or perhaps, in the far future, civilizations might discover ways to extract energy from vacuum fluctuations or other exotic sources. The infinite energy barrier represents one of the most serious obstacles to time travel. It suggests that while the future is accessible, the past might be eternally locked away, protected by the mathematics of physics itself. Time's arrow might be enforced not by law, but by energetic impossibility. Fact 41. Exotic matter with negative mass might be needed. Negative mass is one of the strangest concepts in physics. Regular matter has positive mass. It gravitationally attracts other matter. It resists acceleration according to Newton's laws. But negative mass would behave oppositely. It would gravitationally repel normal matter. If you pushed it, it would accelerate toward you rather than away. Negative mass appears in the equations for traversable wormholes, Alcubierre drives, and other exotic space-time structures. To hold open a wormhole or create a warp bubble, you seemingly need matter that has negative gravitational effects, pushing space-time rather than pulling it. Does negative mass exist? We've never observed it. It seems to violate energy conditions that most physicists believe must hold. If negative mass existed, it might enable perpetual motion machines and other impossible devices. You could accelerate positive and negative masses together, gaining energy from nowhere. Some quantum effects produce something resembling negative energy density in limited contexts. The Casimir effect demonstrates a kind of negative energy between parallel plates in vacuum. But this is far from the large-scale negative mass needed for wormholes or warp drives. Perhaps negative mass is absolutely forbidden by deeper principles, or perhaps it exists in forms we haven't discovered. Maybe dark energy, the mysterious force accelerating the universe's expansion, involves negative pressure that's similar to negative mass in its effects. If negative mass turns out to be impossible, most routes to practical time travel close. Wormholes collapse, warp drives fail. The universe might have structured its laws specifically to prevent the exotic matter needed for time machines. This would be another form of chronology protection, enforced at the level of what types of matter can exist. Fact 42. Casimir effect. Demonstrates negative energy. Exists on quantum scales. The Casimir effect, predicted in 1948 and measured in 1997, demonstrates something extraordinary. Negative energy can exist, at least in specialized quantum contexts. Place two uncharged metal plates very close together in vacuum. Quantum mechanics predicts they'll attract each other. This isn't electromagnetic attraction, it's something stranger. The vacuum between the plates has less energy than the vacuum outside them, creating a kind of negative pressure that pushes them together. This happens because of quantum fluctuations. Even empty space seethes with virtual particles constantly appearing and disappearing. Between the plates, only certain wavelengths of these fluctuations can exist, determined by the gap width. Outside, all wavelengths exist. The difference creates an imbalance, a net pressure. From one perspective, the region between the plates has negative energy relative to normal vacuum. This is significant because many exotic space-time structures, like traversable wormholes, require negative energy. The Casimir effect proves negative energy isn't forbidden by physics. However, the amounts are tiny. The Casimir effect produces negative energy densities far too small to hold open a wormhole or create a time machine. Scaling it up to useful levels seems impossible with any known technology. Still, it's a proof of principle. Nature allows negative energy in specific contexts. Perhaps there are other quantum effects, not yet discovered, that produce stronger negative energy. Perhaps advanced civilizations could manipulate vacuum fluctuations in ways we can't imagine. The Casimir effect keeps the door open, showing that some ingredients for time machines exist in nature, even if we're nowhere close to harnessing them. It's a tiny crack in the barrier, a hint that the impossible might merely be impractical. Fact 40. 3. Time crystals are structures that repeat in time. In 2012, physicist Frank Wilczek proposed an exotic state of matter, time crystals. These are structures that repeat in time, like ordinary crystals repeat in space. Where normal crystals have repeating patterns in their spatial arrangement, time crystals have patterns that repeat temporally. Imagine atoms arranged in a lattice that moves, not through space, but through time. The system returns to its original state periodically, oscillating forever without energy input. It's like a perpetual motion machine, but one that doesn't violate conservation of energy because it exists in its ground state, the lowest energy configuration. Initially, many physicists thought time crystals were impossible. They seemed to violate fundamental symmetries. But in 2016, researchers created time crystals in laboratories using carefully prepared quantum systems. The crystal's properties were exactly as theory predicted. Time crystals aren't useful for practical time travel, but they reveal something fascinating about time's nature. They show that time has structure, that it can have texture and pattern, not just flow uniformly. In a sense, time crystals are temporal rather than spatial objects. They also connect to deeper questions about time symmetry and the arrow of time. Time crystals break temporal translational symmetry, meaning they look different at different times even in their ground state. This suggests time has richer structure than we typically assume. Understanding time crystals might eventually help us comprehend time itself more deeply. They're evidence that quantum mechanics and thermodynamics interact with time in subtle ways. They hint that time might support structures and phenomena we haven't yet imagined, and that the temporal dimension might be stranger and more complex than the spatial ones. Fact 44. Quantum tunneling allows particles to appear to move backward in time. Quantum tunneling is a phenomenon where particles pass through barriers they shouldn't be able to cross according to classical physics. An electron can tunnel through an energy barrier, appearing on the other side without ever having enough energy to climb over it. It's as if it borrowed energy briefly, crossed, and repaid the debt. What makes tunneling relevant to time travel is the speed. When physicists measure how long tunneling takes, they get strange results. Sometimes the time seems to be zero or even negative. The particle appears to exit the barrier before it entered, from certain perspectives. This doesn't mean macroscopic time travel, but it suggests that at quantum scales, causality is more flexible than we thought. Particles don't follow simple paths through space-time. They exist in superpositions, taking all possible paths simultaneously until measured. Some of these paths seem to go backward in time. In quantum field theory, antiparticles are mathematically equivalent to particles traveling backward in time. A positron moving forward can be described as an electron moving backward. This is more than mathematical convenience. It hints at deep connections between time direction and particle properties. Quantum tunneling and related effects show that the quantum world doesn't respect time's arrow the way the macroscopic world does. At tiny scales, over brief moments, time becomes fuzzy, bidirectional, strange. Causes and effects blur together. This raises fascinating questions. Does macroscopic time travel emerge from quantum effects? Could we somehow amplify quantum time reversal to macroscopic scales? Or are these effects fundamentally limited to the quantum realm, unable to scale up? Quantum tunneling suggests time's foundations are stranger than its everyday appearance. Fact 45. Closed causal loops in general relativity permit time travel mathematically. General relativity, Einstein's theory of gravity and spacetime, is expressed through field equations that describe how matter and energy curve spacetime. These equations have many solutions, each representing a possible spacetime geometry, a possible universe. Some solutions contain closed causal loops, paths through spacetime that loop back to their own past. Mathematically, these solutions are just as valid as the solutions describing our universe. They satisfy the equations perfectly. Nothing in the mathematics forbids them. The Gödel universe, rotating black holes, configurations of cosmic strings, certain wormhole geometries, all contain closed causal loops. In these spacetimes, time travel to the past is possible simply by following a world line, a path through spacetime. This is profound. It means Einstein's theory, one of the most successful and fundamental theories in physics, permits time travel. The equations don't rule it out. If we trust general relativity, we must acknowledge that time travel is at least mathematically possible. But mathematics and physical reality don't always align. Just because equations allow something doesn't mean nature does. There might be additional principles, boundary conditions, or quantum effects that eliminate closed causal loops from physical reality, even though they appear in mathematical solutions. Many physicists believe that when we eventually unify general relativity with quantum mechanics into a theory of quantum gravity, closed causal loops will be forbidden. Quantum effects might censor them, enforcing chronology protection at a fundamental level. Still, their presence in general relativity is significant. It shows that spacetime is flexible enough, in principle, to permit time travel. Whether nature exploits this flexibility remains one of physics' deepest open questions. Fact 46. Time perception varies dramatically. Your subjective experience of time isn't constant. Sometimes minutes feel like hours, other times hours vanish like minutes. This isn't just imagination. Your brain's time perception mechanisms are flexible, influenced by attention, emotion, novelty, and neurochemistry. During emergencies, many people report time seeming to slow down. A car accident that takes seconds to unfold feels like it lasts much longer. This happens because your brain records memories more densely during intense experiences. When you recall the event, the richness of detail makes it seem longer than it was. Your attention also affects time perception. When you're focused on time itself, watching a clock, time crawls. When you're absorbed in an engaging task, time flies. This is why boring meetings seem endless while enjoyable activities pass quickly. Neurochemicals play a role too. Dopamine, associated with reward and motivation, affects your internal clock. Higher dopamine levels make time seem to pass slower. Lower levels speed it up. Certain drugs that affect dopamine dramatically alter time perception. Age influences perception too. As you get older, each year represents a smaller fraction of your total life experience. Time seems to accelerate as you age, not because it actually moves faster, but because each moment is proportionally less significant to your accumulated experience. Even body temperature matters. When you're feverish, your internal clock speeds up, making external time seem slower. These variations show that time perception is constructed by your brain, not directly sensed. Understanding subjective time helps us appreciate that the steady flow we experience is partly illusion constructed by neural processes. Objective time, measured by clocks, differs from subjective time experienced by consciousness. Both are real, but they're not the same thing. Fact 47. Children experience time slower than adults. If you've ever noticed that childhood summers seemed endless, but adult summers fly by, you're experiencing a well-documented phenomenon. Children perceive time as passing more slowly than adults do. A year to a 5-year-old feels much longer than a year to a 50-year-old. Several factors contribute to this. First, proportional theory. Each year represents a larger fraction of a child's life. To a 5-year-old, 1 year is 20% of their entire existence. To a 50-year-old, it's only 2%. Proportionally, the year matters more to the child. Second, novelty. Children constantly encounter new experiences. Everything is fresh, surprising, worthy of attention. Their brains encode rich, detailed memories of these novel events. Adults, living in familiar routines, don't encode as many distinct memories. The same amount of clock time produces fewer memorable moments. Third, brain development. A child's brain processes information differently, potentially at different subjective speeds. Neural development and myelination, the insulation of nerve fibers, continue into the 20s. These changes might affect the pace of neural processing and time perception. Fourth, anticipation. Children spend more time looking forward to events. Waiting for birthdays, holidays, or summer vacation makes time drag. Adults, with more immediate control over their lives and less dramatic calendar markers, don't experience the same prolonged anticipation. This means childhood really is a longer experience subjectively, even though it's the same clock duration. Those who say childhood feels eternal aren't wrong. The first decade of life might contain more subjective time than several decades of adulthood. It's a reminder that time is as much psychological as physical. The hours measured by clocks are consistent, but the hours experienced by consciousness vary dramatically based on age, novelty, and circumstance. Fact 48. Memory makes time seem faster as we age. As we age, time appears to accelerate. Years that seemed endless in childhood zoom by in adulthood. This is largely due to how memory works and how we encode experiences. When life is full of novel experiences, your brain creates rich, detailed memories. You're paying attention, encoding information, creating mental landmarks. When you look back, the abundance of memories makes that period seem long. You have many distinct moments to recall. But as we age, life becomes routine. You've driven to work thousands of times. You've made dinner countless evenings. These repeated experiences aren't encoded as separate memories. Your brain lumps them together, creating few distinct recollections. When you look back at a period dominated by routine, you find few memory markers. The time seems short in retrospect because there's little to remember. You can't distinguish Tuesday from Thursday 3 weeks ago. They blur together. This explains why childhood, full of firsts and novel experiences, seems long in memory. First day of school, first friend, first bike ride, everything is new and memorable. Adulthood, with its repetitions and routines, compresses in memory. Months pass with few distinctive moments. The solution is to seek novelty, travel to new places, learn new skills, break routines, create experiences worth encoding. People who maintain novelty in their lives report time feeling slower, richer, more expansive. This shows that memory and time perception are intimately linked. The past isn't stored objectively, but reconstructed from highlights and salient moments. Sparse memories create a sense of brevity. Rich memories create a sense of duration. You can, in a sense, extend your subjective life by living memorably. Fact 49. Dopamine affects time. Perception. Dopamine, a neurotransmitter associated with reward, motivation, and pleasure, plays a surprising role in how you perceive time's passage. Your brain has an internal clock, and dopamine modulates how fast that clock runs. Higher dopamine levels make your internal clock tick faster. When your clock runs fast, external time seems to pass slowly. This is why exciting, dopamine-releasing activities make time feel stretched out. You're experiencing more subjective moments per objective second. Lower dopamine levels slow your internal clock. External time seems to speed up. This might explain why depression, associated with reduced dopamine function, makes time feel like it's rushing by without meaning or texture. Drugs that affect dopamine dramatically alter time perception. Stimulants like amphetamines, which increase dopamine, make time seem to slow down. Users report minutes feeling like hours. Conversely, drugs that block dopamine can make time seem to accelerate. Neurological conditions affecting dopamine also impact time perception. Parkinson's disease, which involves dopamine deficiency, often impairs patients' ability to judge time intervals accurately. They underestimate durations, suggesting their internal clocks run slow. Activities naturally releasing dopamine, like playing games, pursuing goals, or engaging in enjoyable tasks, alter time perception. This is partly why flow states, where you're fully absorbed and dopamine systems are active, distort time. Hours can feel like minutes. Understanding dopamine's role shows that time perception isn't passive, but actively constructed by neurochemical systems. Your sense of duration is a brain-generated experience, modulated by the same systems that govern motivation and reward. Subjective time speeds up or slows down based on your neurochemical state. Fact 50. Body temperature influences. How fast time seems to pass. Your body temperature affects your internal clock in measurable ways. When you're feverish, with elevated body temperature, your internal clock speeds up. More subjective time passes per objective second. External events seem to occur in slow motion. Experiments confirm this. When people's body temperatures are artificially elevated, they overestimate how much time has passed. Ask them to count to 60 seconds, and they count too fast, reaching 60 before a minute actually elapses. Their internal clock is racing. Conversely, when body temperature drops, the internal clock slows. People underestimate durations. They count too slowly, not reaching 60 until more than a minute has passed. This temperature effect is likely rooted in chemistry. Neural processes are chemical reactions, and reaction rates increase with temperature. Warmer neurons fire faster, speeding up the brain's timekeeping mechanisms. This has practical implications. Fever doesn't just make you feel terrible, it actually alters your experience of time's flow. The world outside seems sluggish while your thoughts race. Hypothermia might have the opposite effect, with the world seeming to rush by. Even normal circadian variations in body temperature, which rises and falls throughout the day, might subtly affect time perception. Your sense of duration might shift slightly from morning to evening as your core temperature changes. This physiological connection reminds us that consciousness, including time perception, is embodied. Your subjective experience depends on the physical state of your body and brain. Time isn't just a feature of external reality or pure consciousness, but an interaction between your neural processes and the world, modulated by something as basic as body temperature. Fact 51. The brain predicts the future. About 80 milliseconds ahead. Your conscious awareness of the present moment is actually slightly delayed. By the time you perceive something, your brain has already processed it and prepared responses. But to make this work smoothly, your brain does something remarkable. It predicts the immediate future and presents that prediction as your present experience. Neuroscience suggests this prediction window is about 80 milliseconds. Your brain extrapolates from recent information to construct what it expects to be happening now. This predictive processing makes your experience feel smooth and synchronized, despite neural delays. This is why you can catch a ball. If your conscious perception lagged reality by 80 milliseconds, the ball would be elsewhere by the time you saw it. But your brain predicts the ball's trajectory and positions your hand where it expects the ball to be, not where it was when light from it hit your eyes. This prediction sometimes fails. Optical illusions, unexpected movements, and magic tricks exploit the gap between prediction and reality. When your brain's prediction is wrong, you experience surprise or confusion. The world suddenly doesn't match expectation. In a sense, you're always living slightly in the future, experiencing your brain's best guess about what's happening now. You're never perceiving the absolute present, but a predicted present, constructed from the recent past. This has philosophical implications. If you don't directly perceive the present, but only predictions of it, where does the actual present exist? Is there a true present moment, or just a series of overlapping predictions, with consciousness forever chasing an elusive now? Understanding this prediction mechanism reveals that even ordinary time perception involves a form of time travel. Your brain reaches into the immediate future, constructs an experience, and presents it as now. Every moment of awareness is a small prophecy. Fact 52. Time blindness is real. Some people have difficulty sensing time's passage or estimating durations. This condition, sometimes called time blindness or dyschronometria, isn't about lacking clocks. It's about the internal sense of time itself. Time blindness is associated with conditions like ADHD, where executive function difficulties extend to time management. People with time blindness might genuinely not realize hours have passed. They start a task expecting it to take minutes and look up to find it took hours. They're consistently late, not from irresponsibility, but from inability to gauge duration. The condition suggests that time perception involves specific neural mechanisms that can be impaired. Just as some people are colorblind, unable to perceive certain colors, others might be time blind, unable to perceive duration accurately. Brain regions involved in time perception include the basal ganglia, cerebellum, and prefrontal cortex. Damage or dysfunction in these areas can impair timing. People with certain brain injuries lose the ability to judge intervals or maintain temporal order of events. Time blindness varies in severity. Some people experience mild difficulties, being somewhat worse than average at estimating durations. Others face significant challenges that affect daily functioning, unable to be punctual or plan effectively. Understanding time blindness reminds us that time perception isn't universal. The clock experience that most people take for granted is constructed by specific neural systems. When those systems don't work typically, subjective time becomes unreliable or absent. It's a reminder that time, as we experience it, is as much about neurology as physics. The steady flow of moments depends on brain function. Impair the right circuits, and time becomes slippery, unreliable, or altogether absent from consciousness. Fact 53. Chronesthesia is the ability to mentally time travel. Chronesthesia is the brain's ability to mentally travel through time, to remember the past and imagine the future. It's sometimes called mental time travel, and it's considered a hallmark of human consciousness, though some animals might possess versions of it. When you remember yesterday or plan for tomorrow, you're engaging chronesthesia. You project your consciousness backward or forward in time, re-experiencing or pre-experiencing events from a subjective perspective. You don't just know facts about the past or future, you simulate experience of them. This ability depends on the hippocampus and related brain structures. People with hippocampal damage, like amnesia patient HM, lose both the ability to form new memories and to imagine future scenarios. The same neural systems support both backward and forward mental time travel. Chronesthesia involves several cognitive capacities: episodic memory, which stores personal experiences, prospection, imagining future events, and self-projection, placing yourself mentally in different times. These abilities seem uniquely developed in humans, though some evidence suggests other animals, like corvids and great apes, might possess basic versions. This mental time travel isn't the same as physical time travel, but it's remarkable nonetheless. You can revisit childhood, replay conversations, or rehearse tomorrow's presentation. You can plan for years ahead, imagining your future self's circumstances. Some philosophers argue chronesthesia is essential to human identity. Your sense of being a continuous person across time depends on mentally connecting your past, present, and future selves. Without chronesthesia, you might live only in an eternal now without autobiography or anticipation. Understanding chronesthesia reveals that humans are temporal creatures, not just physically, but psychologically. We inhabit time through memory and imagination as much as through forward-flowing bodily existence. Fact 54. Cannabis alters time perception. Cannabis use produces well-documented alterations in time perception. Users commonly report that time seems to slow down dramatically. Minutes feel like hours. A song seems to last forever. This distortion is one of the drug's characteristic subjective effects. The mechanism involves cannabinoids affecting neural timing circuits. Cannabis primarily acts on CB1 receptors throughout the brain, including regions involved in timekeeping like the basal ganglia and cerebellum. Disrupting these circuits alters the brain's internal clock. Research suggests cannabis might disrupt the brain's ability to maintain attention on time itself. You lose track of how much time has passed because you're not encoding temporal information normally. Without regular temporal landmarks, durations seem extended. Cannabis also affects memory formation, making it harder to recall what just happened. This memory disruption might contribute to time distortion. Without clear memories of recent moments, the recent past seems more distant, stretching subjective time. The effect varies with dose and individual response. Some users report only mild time distortion. Others experience dramatic effects where minutes genuinely feel like hours. The experience can be pleasant or unsettling depending on context and expectations. Interestingly, when asked to estimate intervals, cannabis users typically overestimate duration. If you ask them to signal when 30 seconds have passed, they signal too early. Their internal clock is running fast, making external time seem slow. Cannabis-induced time distortion demonstrates how fragile and constructed time perception is. A molecule interacting with receptors in your brain can dramatically alter your experience of duration. Time isn't directly perceived, but assembled by neural processes vulnerable to disruption. Fact 55. Fear slows perceived time. During frightening experiences, time seems to slow down. A car swerving toward you, a slip on ice, a sudden threat. These moments often feel stretched out, occurring in slow motion. Many people report this phenomenon during near-death experiences or emergencies. This doesn't mean time actually slows. It's a memory effect. During intense fear, your brain's threat response system activates, triggering heightened attention and denser memory encoding. The amygdala, central to fear processing, enhances memory formation for emotional events. You experience the event normally, but you form unusually rich memories of it. When you recall the experience, the abundance of detail makes it seem like more time passed. You remember noticing things you normally wouldn't, experiencing more distinct moments per second. Researchers tested this by dropping volunteers in a free fall and asking them to read rapidly flickering numbers during the fall. If time truly slowed perceptually, they should have been able to read faster numbers. But they couldn't. Their perception during the event was normal. However, after the fall, everyone reported time seeming slowed down. The memory of the fall felt stretched. This confirms it's a retrospective effect, not a real-time perceptual slowing. Fear-induced time dilation might be adaptive. In dangerous situations, encoding rich memories helps you learn from and avoid future threats. Remembering threats in detail improves survival. The experience of slowed time is a side effect of enhanced memory formation. This phenomenon reveals the relationship between emotion, memory, and time perception. Strong emotions don't just color experience, they change how that experience is remembered and how the duration is retrospectively perceived. Emotional intensity creates temporal intensity in memory. Fact 56. The oddball effect makes unexpected events seem longer. Show someone a series of identical images, then suddenly show a different image. Ask how long the different image appeared. People consistently report it lasted longer than the identical images, even though all appeared for the same duration. This is the oddball effect. Unexpected or unusual events seem to last longer than ordinary ones. A novel stimulus captures attention, triggering deeper processing and richer encoding. This creates the retrospective illusion that more time passed. The oddball effect is related to why time seems to slow during first experiences. Your first flight, first day at a new job, or first visit to a foreign country feels longer than later repetitions. Novelty stretches subjective time. This effect contributes to why childhood seems long. For children, most experiences are oddballs, novel, and attention-grabbing. Adults, encountering fewer true firsts, experience fewer oddball events and thus less subjective temporal extension. The oddball effect demonstrates that time perception isn't passive measurement, but active construction. Your brain doesn't have a clock that directly measures duration. Instead, it infers duration from how much was experienced, how much attention was paid, how many memories were formed. Understanding this effect has practical applications. To make life feel longer, seek novelty, break routines, notice details, pay attention. The more you encode, the longer the time will feel in retrospect. A life of routine compresses in memory. A life of attention and novelty expands. The oddball effect is evidence that you have some control over subjective time. Not physical time, but how much life you experience within that time. Richness of experience creates richness of temporal perception. Fact 57. Flow states alter time. Perception. Flow is a psychological state of complete absorption in an activity. Athletes call it being in the zone. Musicians, artists, and programmers experience it during deep creative work. Time perception changes dramatically during flow. In flow states, hours can pass like minutes. You look up from your work and realize it's evening when you thought it was still morning. Time flies, disappearing entirely from awareness. This happens because attention is completely focused on the task, leaving no attention for monitoring time itself. Flow involves several neurochemical changes. Dopamine and norepinephrine levels increase. The prefrontal cortex, involved in self-consciousness and time monitoring, shows reduced activity. You stop thinking about yourself or time, becoming one with the activity. The distortion can be so complete that people in flow report surprise when they realize how much time passed. The experience feels timeless, eternal, yet later they discover hours elapsed. It's one of the most dramatic alterations of time perception available without drugs or brain injury. Flow states are generally positive experiences associated with peak performance and satisfaction. The loss of time sense isn't distressing, but liberating. You escape time's pressure, living purely in the engaged present. Achieving flow requires matching task difficulty with skill level. Too easy, and you're bored. Too hard, and you're anxious. In the sweet spot, where challenge and ability align, flow emerges and time disappears. Understanding flow shows that consciousness can transcend normal time awareness. You can live outside time, at least subjectively, not through technology or physics, but through psychological state. The most profound time travel might be into the eternal now of complete engagement. Fact 58. Schizophrenia can disrupt the sense of past, present, and future. Schizophrenia, a serious mental illness affecting thought and perception, often disrupts time perception. People with schizophrenia may experience difficulties distinguishing past from present, struggle to sequence events correctly, or feel time moving at abnormal speeds. Some patients report time feeling fragmented, with no smooth flow between moments. Others experience temporal compression, where long periods seem instantaneous, or temporal expansion, where seconds feel like hours. The disorder can fundamentally alter the subjective structure of time. This might relate to disrupted neural timing circuits and attention systems. Schizophrenia involves widespread brain changes affecting many regions, including those involved in time perception. Dopamine system dysregulation, central to schizophrenia, also affects internal clocks. Some patients experience difficulties with chronesthesia, mentally traveling through time. They might struggle to recall events in proper order or imagine future scenarios coherently. Their autobiographical timeline becomes confused or disconnected. These temporal disruptions contribute to the disorder's cognitive and functional impairments. If you can't reliably order events or judge durations, planning and remembering become extremely difficult. Normal daily functioning depends on intact time perception. Studying schizophrenia's effects on time reveals how constructed and fragile temporal experience is. The smooth flow of moments from past through present to future depends on complex neural processes. Disrupt them, and time itself becomes chaotic, unreliable, or alien. It reminds us that the stable temporal flow most people experience is an achievement, a construction maintained by specific brain systems. When those systems malfunction, the very fabric of experienced reality, including time, can unravel. Fact 59. Meditation can change. Subjective experience of time. Meditation, particularly mindfulness practices, alters time perception in distinctive ways. Experienced meditators often report time feeling slower, more spacious, more present. Minutes of meditation can feel like extended periods of deep rest. This happens through several mechanisms. Meditation trains attention, making you more aware of each moment. With greater attention density, you encode more experience per objective second, creating subjective temporal expansion. You notice more, so more seems to happen. Meditation also reduces mind wandering and future-focused thinking. Normally, your mind jumps between past and future, spending little time in the actual present. Meditation anchors you in now. This creates a different temporal experience, less rushed, more settled. Some advanced meditators report moments of timelessness, where time seems to stop or become irrelevant. These experiences might involve reduced prefrontal activity, the same pattern seen in flow states. Self-consciousness and time monitoring fade, leaving only present experience. Research shows meditators are better at estimating durations accurately. Their internal clocks seem better calibrated. They're less susceptible to temporal illusions and distortions. Regular practice apparently improves time perception systems. Meditation might offer a form of psychological time travel, moving you more fully into the present moment. While physics focuses on past and future time travel, meditation explores the neglected present, deepening and expanding the now. Understanding meditation's effects on time shows that subjective temporal experience is trainable. You can, through practice, alter how you experience duration, presence, and the flow of moments. Time perception is a skill, not just a given feature of consciousness. Fact 60. Your brain edits reality. Your memories aren't video recordings. Every time you remember something, your brain reconstructs it from fragments, filling gaps with inferences and expectations. This means your past, as you remember it, is partly fiction. Your brain edits your timeline. Research shows memories are malleable. Each time you recall an event, you slightly alter the memory. Details change, the emotional tone shifts. Elements from other events might intrude. Over years, memories can transform dramatically while feeling completely accurate. This editing extends to time perception. When you estimate how long ago something happened, you're not accessing a timestamp. You're inferring duration from context, from how much seems to have happened since, from how vivid or faded the memory feels. Studies demonstrate people commonly misremember event timing. You might think something happened months ago when it was actually weeks, or vice versa. Major life events create temporal landmarks that distort surrounding time. Everything before your wedding seems further back than it was. Everything after seems more recent. Even the order of events can be misremembered. Your brain sometimes rearranges sequences, especially if they make more narrative sense in a different order. The story you tell yourself about your past might not match what actually happened. This isn't malfunction, it's feature. Remembering isn't about perfect archiving, but about extracting meaning, maintaining coherent narratives, and guiding future behavior. Perfect accuracy is less important than useful reconstruction. Understanding memory's fallibility means recognizing that your personal history is partly creative writing. The timeline you inhabit is constructed, edited, revised. Your past is less discovered than invented, shaped by present needs and perspectives. Time, at least personal time, is always being rewritten. Fact 61. Ancient cultures viewed time cyclically. Modern Western culture typically views time as linear, moving irreversibly from past through present to future. This seems natural, but it's culturally specific. Many ancient cultures viewed time differently, seeing it as cyclical, repeating in endless patterns. Ancient Hinduism and Buddhism embrace cyclical time. The universe goes through endless cycles of creation, existence, and destruction. Yugas, vast time periods, repeat forever. Individual souls reincarnate through countless lives. Time is a wheel, not an arrow. Ancient Greeks had two concepts of time: chronos, linear measurable time, and kairos, the right moment, qualitative time. Some Greek philosophers, like the Stoics, believed in eternal recurrence, where the entire universe repeats identically forever. Many indigenous cultures organize time around natural cycles, seasons, agricultural rhythms, celestial movements. Rather than abstract units marching forward, time is the return of planting season, the cycle of ceremonies, the rotation of the stars. Cyclical time perception has profound implications. It suggests nothing is truly new. Everything has happened before and will happen again. This can be comforting, suggesting cosmic order and meaning, or it can feel limiting, denying genuine novelty or progress. The shift to linear time in Western culture relates to Judeo-Christian theology, which sees history moving toward ultimate fulfillment, and to scientific revolution, which emphasized progress and irreversible processes. Neither view is objectively correct. They're frameworks for understanding experience. Linear time emphasizes change, progress, and irreversibility. Cyclical time emphasizes patterns, return, and continuity. Both capture aspects of reality. Time contains both linear and cyclical elements, arrows and circles, depending on what you're observing. Fact 62. H.G. Wells popularized time travel in fiction. In 1895, H.G. Wells published The Time Machine, a novella that fundamentally shaped how we think about time travel. While not the first story featuring time travel, Wells's work popularized the concept and established many enduring tropes. Wells imagined time as a dimension like space, one that could potentially be navigated with technology. His time traveler builds a machine that moves through time like a vehicle moves through space. This mechanical, technological approach to time travel became standard in science fiction. The novel explored profound themes: social evolution, class division, entropy, and the far future of humanity. Wells used time travel not just as adventure, but as social commentary and philosophical exploration. Time travel became a lens for examining human nature and civilization. Wells's influence was enormous. After The Time Machine, time travel became a major science fiction theme. Countless stories, films, and shows followed, exploring paradoxes, alternate histories, and temporal adventures. The genre Wells established has become massive. Fact 63. Mark Twain wrote about time travel. Before H.G. Wells, American author Mark Twain explored time travel in his 1889 novel, A Connecticut Yankee in King Arthur's Court. The story follows a 19th century American who's knocked unconscious and wakes up in medieval England. Twain used time travel for satire and social commentary. His protagonist brings modern knowledge and technology to the past, creating humorous and sometimes dark situations. The novel questions ideas of progress, comparing modern and medieval societies in unflattering ways. Unlike later science fiction, Twain didn't explain the time travel mechanism. It happens mysteriously, almost magically. The focus wasn't on how time travel works, but on what happens when different eras collide, when modern sensibilities meet medieval customs. The novel established the fish out of water narrative that became common in time travel stories. The displaced person struggling to adapt, using future knowledge in the past, trying to change history. These became standard elements of the genre. Twain's work shows that time travel has long fascinated writers as a tool for examining society. By placing characters in different times, authors can highlight contrasts, question assumptions, and explore how history shapes human nature. Time travel becomes a mirror, reflecting our own time back to us. The novel's lasting influence appears in countless later works. The basic premise, modern person in the past, has been repeated endlessly with variations. Twain helped establish time travel as a legitimate literary device, not just for adventure, but for serious social and philosophical exploration. His contribution reminds us that time travel captures imagination, not just scientifically, but culturally and artistically. It's a concept that bridges physics and philosophy, science and storytelling, offering endless possibilities for exploring human experience across time's vast expanse. Fact 64. The Philadelphia Experiment was an alleged military time travel event. The Philadelphia Experiment is an alleged military experiment from October 1943. According to legend, the US Navy attempted to make the destroyer escort USS Eldridge invisible to radar at the Philadelphia Naval Shipyard. Instead, the ship allegedly became invisible to the eye, teleported to Norfolk, Virginia, and time-traveled briefly. Crew members supposedly suffered horrific effects. Some were said to be fused with the ship's hull. Others went insane or disappeared entirely. Some allegedly became invisible themselves. The stories are dramatic and disturbing, involving both space and time displacement. There's no credible evidence the experiment occurred. The Navy denies it. Researchers have debunked the claims. The ship's logs show it wasn't at Philadelphia during the alleged dates. Crew members who could be located denied anything unusual happened. The story likely originated from misunderstood experiments with degaussing, making ships' magnetic signatures invisible to magnetic mines, not visual invisibility. Later embellishments and a hoax book turned this into tales of teleportation and time travel. Despite debunking, the Philadelphia Experiment persists in popular culture. It appears in books, movies, and conspiracy theories. It represents the public's fascination with secret military experiments and the possibility of exotic physics breakthroughs. The legend reveals something interesting about time travel's cultural status. People want to believe it's possible, that somewhere in classified programs, the technology exists. Time travel represents ultimate power, the ability to transcend ordinary limitations. The Philadelphia experiment, though fiction, reflects real hopes and fears about technology, government secrecy, and the manipulation of reality itself. It's a modern myth, expressing timeless desires wrapped in 20th century military technological imagery. Fact 65. John Titor claimed to be a time traveler from 2036. In the year 2000, an internet user named John Titor appeared on online forums claiming to be a time traveler from the year 2036. He posted detailed accounts of his time, his mission, and how time travel worked, creating one of the internet's most famous mysteries. Titor claimed he traveled back to retrieve an IBM computer from 1975, needed to debug legacy systems in his time. He posted technical descriptions of his time machine, based on rotating black holes and something called Tipler cylinders. He included diagrams and specifications. He made predictions about the future, a civil war in the United States starting around 2005, World War III involving Russia, significant changes to the world map. Most predictions didn't come true, at least not in our timeline. Titor claimed multiple timelines exist, so his future might differ from ours. His posts were sophisticated, internally consistent, and detailed. He answered questions thoughtfully, maintaining his story for months before disappearing in March 2001. He claimed to return to his own time, never posting again. Investigators later concluded John Titor was likely a hoax, possibly created by entertainment lawyers. The writing style, knowledge base, and some details suggested it was fiction, not genuine time travel. But the mystery captivated thousands. The Titor case illustrates the internet age's new folklore. Digital spaces create opportunities for elaborate hoaxes and collaborative storytelling. Time travel claims find audiences willing to believe or at least enjoy the story. Titor's legacy endures in internet culture. Whether hoax or reality, the story raised interesting questions about time travel, timelines, and how we'd recognize a genuine time traveler if one appeared. Fact 66. Nostradamus supposedly saw the future. Michel de Nostradame, known as Nostradamus, was a 16th century French physician and astrologer who published collections of prophecies. His writings, particularly Les Prophéties, contain verses supposedly predicting future events centuries ahead. Believers claim Nostradamus predicted numerous historical events: the French Revolution, Napoleon's rise, Hitler's tyranny, the assassination of John F. Kennedy, the September 11 attacks. The prophecies are vague, written in cryptic four-line verses called quatrains, allowing broad interpretation. Skeptics point out the predictions are so vague they can fit almost anything. People interpret them after events occur, finding matches through flexible reading. Prophecies that don't match anything are ignored. This is confirmation bias, seeing patterns where none exist. Nostradamus likely didn't time travel or genuinely see the future. He studied astrology and medicine, writing prophecies following traditions of his time. His verses may reflect educated guesses about politics and patterns he observed, expressed poetically and obscurely. Yet his fame endures. Each generation finds new meanings in his verses, applying them to contemporary events. Nostradamus has predicted events from every century since his death. The prophecies are Rorschach tests, revealing more about interpreters than the future. The Nostradamus phenomenon shows humanity's desire to know the future. We seek patterns, signs, predictions. We want to believe someone glimpsed what's coming, providing warning or comfort. Even weak evidence gets amplified when it confirms this desire. Whether time travel, precognition, or clever poetry, Nostradamus represents our eternal fascination with tomorrow. We scan the past for clues about the future, hoping someone, somewhere, managed to peer beyond the present moment into time yet to come. Fact 67. Time travel appears in virtually every culture's mythology. Time travel, in various forms, appears across cultures throughout history. Ancient myths and legends contain stories of people visiting the future, returning to the past, or experiencing time differently than normal. The concept predates modern science by millennia. Japanese legend tells of Urashima Taro, a fisherman who rescues a sea turtle. The turtle takes him to an underwater palace where he stays for what seems like 3 days. When he returns home, 300 years have passed. His village is unrecognizable, his family long dead. Irish mythology includes stories of Tir na Nog, the land of eternal youth, where time moves differently. Heroes visit and spend what feels like a year, only to discover centuries passed in the mortal world. Touching earthly ground causes them to age instantly, centuries catching up at once. Hindu texts describe yogis and sages experiencing time differently through meditation and spiritual practices. Some attain states where they witness past and future simultaneously. Time becomes fluid, navigable through consciousness rather than technology. Buddhist philosophy contains concepts of time as illusion, with past, present, and future existing simultaneously in ultimate reality. Advanced practitioners supposedly transcend ordinary temporal experience. Native American traditions include vision quests and shamanic journeys where time behaves strangely, where spirits show past and future events, where days pass like moments, or moments stretch into eternities. These recurring themes across unconnected cultures suggest something deep about human psychology. We've always wondered about time's nature, always imagined transcending its flow. Time travel isn't a modern invention, but an ancient dream, expressed through each culture's unique mythology and worldview. Fact 68. Buddhist philosophy suggests past, present, and future exist simultaneously. Buddhist philosophy, particularly in some Mahayana traditions, proposes that past, present, and future aren't truly separate. They're divisions created by ordinary consciousness, but in ultimate reality, all times exist together in an eternal now. This connects to the Buddhist concept of emptiness and interdependence. Nothing exists independently. Everything connects to everything else across space and time. The present contains the past as causes and the future as potentials. Past, present, and future interpenetrate. Some Buddhist texts describe advanced meditation states where practitioners perceive past and future directly. They see their past lives, understand karmic connections spanning centuries, and glimpse future consequences of present actions. Time becomes transparent, navigable through consciousness. This isn't time travel in the physical sense, but a different relationship with temporality. Rather than moving through time, consciousness expands to encompass multiple times simultaneously. The practitioner doesn't change location in time, but changes their perspective on it. Buddhist philosophy also emphasizes impermanence. Everything changes constantly. The self you were a moment ago is gone. The self you'll be tomorrow doesn't exist yet. In this view, time is a series of momentary arising and ceasing, not a continuous flow. These ideas resonate with some modern physics interpretations. The block universe theory suggests past, present, and future all exist timelessly in four-dimensional space-time. Only consciousness creates the illusion of flow, moving through this static structure. Whether Buddhist insights are metaphysical truth, phenomenological description, or poetic philosophy, they offer a radically different way of understanding time. They suggest our ordinary temporal experience might not be ultimate reality, and that other relationships with time are possible through transformation of consciousness itself. Fact 69. Jules Verne imagined many technologies before they existed. Jules Verne, the 19th century French novelist, imagined technologies and scenarios that seemed like pure fantasy, but later became reality. His works appear almost prophetic, as if he saw into the future and described what he found there. In From the Earth to the Moon, written in 1865, Werner described sending humans to the moon in a projectile launched by a giant cannon. While the method differs from actual spaceflight, the location of the launch, Florida, and the splashdown in the Pacific Ocean eerily match the actual Apollo missions a century later. In 20,000 Leagues Under the Sea, he described the Nautilus, an advanced submarine capable of extended underwater voyages. Real submarines followed decades later, with nuclear submarines eventually matching the Nautilus's capabilities. He wrote about air travel, video conferencing, tasers, solar sails, and skywriting before any existed. His imagination consistently anticipated technological development, not through time travel or psychic powers, but through extrapolating from contemporary science and engineering trends. Verne studied science extensively and understood engineering principles. His predictions weren't random guesses, but informed extrapolations. He asked, if we extend current trends, what becomes possible? This rational imagination created accurate forecasts. His success demonstrates that seeing the future sometimes means understanding the present deeply and projecting forward logically. The future isn't completely unknowable. It grows from the present. Careful observers can discern emerging patterns and possibilities. Verne's legacy suggests that science fiction isn't just entertainment, but exploration. Authors imagine possibilities that engineers later realize. Fiction and reality influence each other across time, with stories inspiring inventors who create the very technologies that were imagined. It's a creative time loop spanning generations. Fact 70. The Mandela effect suggests false memories of timeline changes. The Mandela effect refers to situations where large groups of people remember events differently than documented evidence shows. The name comes from false memories many people have of Nelson Mandela dying in prison in the 1980s, when he actually died in 2013. Other examples include people remembering the Berenstain Bears as Berenstein, or the movie line, "Luke, I am your father," when Darth Vader actually says, "No, I am your father." Thousands share these false memories, remembering details that evidence shows never existed. Some attribute this to parallel timelines or reality shifts. They suggest we remember alternate timelines where events occurred differently. Perhaps reality changed, or we shifted between parallel universes, bringing memories from one timeline into another. The scientific explanation is less exotic but fascinating. False memories form through suggestion, reinforcement, and how memory works. We don't record reality directly, but reconstruct it from fragments. Our brains fill gaps with plausible details that may be wrong. When many people share false memories, it's often because they share similar contexts, sources of misinformation, or cognitive biases. The false memory spreads like a virus through cultural transmission, each person reinforcing it for others. The Mandela effect reveals memory's unreliability. We trust our memories as factual records, but they're reconstructions, vulnerable to error and suggestion. Large groups can be collectively wrong while feeling completely certain. Whether evidence of timeline shifts or memory fallibility, the Mandela effect shows our relationship with past reality is more complex than we assume. The past we remember may not be the past that actually occurred, creating a personal form of time distortion where our minds inhabit slightly different histories than what actually happened. Fact 71. Déjà vu might be a brain glitch or glimpse of repeated timelines. Déjà vu, French for already seen, is the eerie feeling that you're experiencing something you've experienced before. You enter a new place, but it feels familiar. A conversation feels like a replay. It's as if you're reliving moments from the past or from another timeline. Scientific explanations suggest déjà vu results from neural misfiring. Your brain's memory systems might briefly malfunction, creating false familiarity. One hypothesis suggests a momentary delay between perception and conscious awareness, making the present feel like a memory. Another theory involves similarity matching. The current situation resembles a past experience in subtle ways your conscious mind doesn't recognize. Your subconscious detects the similarity, creating a feeling of familiarity without specific recall. Some neurological conditions increase déjà vu frequency. Temporal lobe epilepsy often causes intense, prolonged déjà vu experiences. This suggests the phenomenon involves specific brain regions, particularly those processing memory and familiarity. More speculative theories connect déjà vu to precognition or parallel timelines. Perhaps you're remembering dreams where you previewed this moment, or maybe you're experiencing overlap with parallel versions of yourself living similar but slightly different lives. Some suggest déjà vu could relate to closed time-like curves, moments where time loops back on itself. You're experiencing something for the second time because timeline loops make it actually repeat, though you don't consciously remember the first iteration. While scientific explanations seem most plausible, the experience remains mysterious and unsettling. That feeling of impossible familiarity, of living through a moment that shouldn't be familiar, hints at something strange about consciousness, memory, and time's nature. Whether glitch or glimpse, déjà vu reminds us that our experience of time contains mysteries we haven't fully explained. Fact 72. Precognition studies have shown statistically significant results. Precognition, knowing the future before it happens, seems impossible. Yet some scientific studies have reported statistically significant results suggesting precognitive effects, however small and controversial. Psychologist Daryl Bem published studies in 2011 where participants seemed to anticipate random future events at rates above chance. The studies were controversial, criticized for methodology and statistical approaches, but they met standard scientific publication criteria. Other research into presentiment suggests people's physiology responds to emotional stimuli seconds before the stimuli are randomly selected and shown. Heart rate and skin conductance change before participants could possibly know what's coming. Effect sizes are small, but statistically significant in some studies. Skeptics argue these results reflect statistical artifacts, experimental flaws, or publication bias, where positive results get published, while negative results don't. The effects haven't been reliably replicated, and no mechanism explains how precognition could work. Believers suggest quantum mechanics might allow retrocausal effects, future events influencing the past on microscopic scales that occasionally bubble up to psychological phenomena. Or perhaps consciousness operates partly outside normal time. The scientific consensus is skeptical. Extraordinary claims require extraordinary evidence, and precognition evidence remains weak, inconsistent, and unexplained. Most likely, apparent precognition reflects bias, coincidence, and statistical flukes. Still, the possibility tantalizes. If even tiny precognitive effects exist, they'd revolutionize our understanding of causality and time. They'd suggest the future reaches back to influence the present in ways we don't understand. The research continues, controversial and inconclusive, probing the boundaries between impossible and merely improbable. Fact 73. The Simpsons has predicted numerous future events. The Simpsons, the long-running animated sitcom, has seemingly predicted numerous future events with eerie accuracy. From Donald Trump's presidency to smartwatches to autocorrect failures, the show appears to forecast the future decades ahead. In a 2000 episode, the show depicted Donald Trump as president, with the episode showing Lisa dealing with Trump's financial legacy. 16 years later, Trump became president. Other predictions include video calling, voted rigging machines, Disney buying Fox, and even the discovery of the Higgs boson. Is this time travel, precognition, or something else? The explanation is probably more mundane but interesting. The Simpsons has produced over 700 episodes across more than 30 years. With that much content satirizing contemporary trends, some predictions will hit simply by chance. The writers are also well educated, observing politics, technology, and culture closely. Their predictions often extrapolate current trends. Trump had discussed presidential ambitions for years before the episode aired. Video calling was anticipated in science fiction for decades. These aren't impossible forecasts, but informed guesses about where things were heading. There's also confirmation bias. People remember hits and forget misses. The show made countless predictions that didn't come true, but those are forgotten. The accurate ones become famous, creating an illusion of prophetic powers. Finally, the show influences culture. When millions watch a scenario on The Simpsons, it enters collective consciousness. Sometimes reality imitates fiction, with people creating what they saw imagined. The show helps create the future it appears to predict. The Simpsons phenomenon shows how pattern recognition, confirmation bias, and cultural influence create apparent time travel. It's not prophecy, but probability, observation, and feedback loops between fiction and reality across time. Fact 74. Art and literature may influence future inventors. Science fiction has repeatedly inspired real technology. Star Trek's communicators influenced cell phone design. Tablet computers appeared in science fiction decades before iPads. Authors imagine technologies that engineers later build, creating a creative feedback loop across time. This raises interesting questions about causality. Did science fiction predict the future or create it? When inventors grew up reading about certain technologies, did those stories plant seeds that grew into actual innovations? Many scientists and engineers cite science fiction as inspiration. Arthur C. Clarke's satellite communications concept influenced real satellite development. Isaac Asimov's robot stories shaped robotics ethics discussions. William Gibson's cyberspace influenced internet development. This creates something like a causal loop. Writers imagine technologies without necessarily knowing how they'd work. Readers inspired by these stories pursue careers in science and engineering. They work to realize the imagined technologies. The fiction causes the reality it depicted, but it's not deterministic. Fiction imagines many technologies that never materialize. Flying cars, teleportation, faster than light travel remain fictional despite decades of imagination. Some technologies are possible and get built. Others remain impossible or impractical. The relationship between fiction and reality demonstrates that the future isn't completely determined or completely open. It's shaped by imagination, possibility, and effort. Writers exploring future possibilities help create those futures by inspiring the people who'll build them. This is a form of time travel through culture and influence. Ideas travel forward, changing the future by existing in the present. Stories become self-fulfilling prophecies, not through magic, but through inspiration. Art doesn't predict the future so much as help create it, sending messages forward that reshape what's possible. Fact 75. Time capsules are our way of sending messages to the future. Time capsules represent a simple but profound form of time travel. We seal objects, documents, and messages in containers, bury or hide them, and wait for future people to discover them. It's one-way communication across time, sending pieces of the present into the future. Time capsules have existed for centuries, though the term is modern. Ancient civilizations left caches of objects, sometimes intentionally for future discovery. Cornerstone time capsules in buildings date back centuries, containing newspapers, coins, and documents for future builders or archaeologists. Modern time capsules range from small personal projects to major public undertakings. The Crypt of Civilization, sealed in 1940 at Oglethorpe University, contains artifacts representing early 20th century life, intended to be opened in 8113, 6,000 years later. The appeal is obvious. We want to speak to the future. We want future people to know we existed, what we valued, how we lived. Time capsules are messages across the temporal void, hoping for an audience we'll never meet. They also reveal assumptions about the future. We assume civilization will continue, that future people will find and value our capsules, that they'll understand our languages and technologies. These assumptions aren't guaranteed. Many time capsules have been lost, forgotten, or become unreadable. Digital time capsules face unique challenges. Will future people have devices to read our storage media? Will file formats be readable? Digital preservation is harder than physical, as technologies become obsolete within decades. Time capsules are bittersweet. They acknowledge we won't experience the future, but want to touch it somehow. They're our way of reaching forward, hoping for connection across time's one-way flow, sending artifacts and messages like bottles into the ocean of future time. Fact 76. We're all time, traveling into the future at 1 second per second. Here's the most mundane, yet most profound fact about time travel. You're doing it right now. You're traveling into the future at the rate of 1 second per second. Every moment, you move forward through time, leaving the past behind and entering the future. This might seem trivial, but it's worth contemplating. You're a time traveler by definition. You exist in the present, but that present constantly becomes past as you slide forward into future moments. Your life is a journey through the fourth dimension. You can't stop this motion. You can't pause time or reverse it through ordinary means. You're locked into forward motion through time, experiencing one moment after another in sequence. This forward flow is time's arrow, the direction of causality and entropy increase. What makes us time travelers is consciousness. We remember the past, experience the present, and anticipate the future. We carry our timeline with us, aware of our journey through time in ways other objects aren't. A rock moves through time too, but without awareness. Our constant forward motion raises philosophical questions. Is the future already determined, waiting for us to reach it? Or does it come into existence as we arrive? Are we moving through time, or is time moving through us, creating new moments constantly? You're also time traveling at different rates depending on your motion and gravity. Move faster or closer to massive objects, and you time travel into the future slightly faster, aging more slowly than others, but you never stop time traveling forward. Recognizing yourself as a time traveler can shift perspective. Each moment is both familiar, as you've been time traveling your whole life, and precious, as you can't revisit it. You're on a one-way journey through time, and this moment, right now, is your current location on that journey. Fact 77. Looking at stars is looking into the past. When you look at the night sky, you're seeing the past. Starlight takes years, decades, or millennia to reach Earth. The stars you see aren't as they are now, but as they were when their light began its journey. The nearest star system, Alpha Centauri, is about 4.3 light years away. When you see it, you're seeing it as it was 4.3 years ago. If something happened there today, you wouldn't know for over 4 years. More distant stars show even older light. Betelgeuse, a red supergiant, is about 600 light years away. The light you see tonight left Betelgeuse around 1400 during Earth's medieval period. If Betelgeuse exploded today, we wouldn't see it until around 2600. Some visible stars might not even exist anymore. They could have died centuries ago, but their final light hasn't reached us yet. We're seeing ghosts, images of objects that may be gone. Looking deeper, telescopes can see galaxies billions of light years away. The light from these galaxies began its journey when the universe was young, showing us not just distant space, but ancient time. We're seeing these galaxies as they were billions of years ago, possibly long before Earth existed. This makes telescopes into time machines of a sort. Looking farther into space means looking farther into the past. The universe has no universal now. There's no moment that's simultaneously present everywhere. Distance creates temporal separation. This everyday form of time travel to the past reminds us that space and time are intimately connected. You can't separate them. When we observe the universe, we're always observing history, seeing light that's been traveling through time to reach us, bringing news from the past. Fact 78. The observable universe shows us 13.8 billion years of cosmic history. The universe is about 13.8 billion years old. Light travels at finite speed, so we can only see objects whose light has had time to reach us since the Big Bang. This creates the observable universe, a sphere centered on Earth containing everything we can possibly see. Looking at distant objects means looking into the past. The cosmic microwave background, the afterglow of the Big Bang, shows the universe as it was 380,000 years after its birth. When we observe this radiation, we're seeing almost a time's beginning. Distant galaxies appear as they were billions of years ago. When the universe was young, stars were forming rapidly and galaxies were colliding and merging. We see cosmic evolution, the universe changing and developing across vast timescales. This gives us a unique perspective. We can observe the universe at different ages simultaneously. Nearby galaxies show recent time. Distant galaxies show ancient time. By comparing them, we watch the universe age, seeing its entire history spread across space. The edge of the observable universe shows light from objects as they were nearly 14 billion years ago, shortly after the Big Bang. Those objects have evolved enormously since then. If we could see them as they are now, they'd look completely different. But that light won't reach us for billions more years. This means the universe is much larger than what we can observe. The total universe might be infinite. But we're limited to our observable bubble, a sphere of causally connected space-time, roughly 93 billion light-years across, accounting for expansion. The observable universe is essentially a time machine, showing us cosmic history. By looking at different distances, we observe different eras. Astronomy becomes archaeology, excavating the past through light that's been traveling across space and time to reach us. Fact 79. The Andromeda Galaxy appears as it was. 2.5 million years ago, Andromeda, our nearest large galactic neighbor, appears in Earth's night sky as a faint smudge. What you're seeing is light that left Andromeda about 2.5 million years ago, during Earth's Pliocene epoch, when human ancestors were just beginning to use stone tools. Andromeda today is different from the Andromeda we see. Stars have been born and died. The galaxy has continued its slow rotation. Individual stars have moved, changed brightness, or evolved to new stages. But we won't see today's Andromeda for 2.5 million years. If an alien civilization in Andromeda pointed a telescope at Earth right now, they wouldn't see modern civilization. They'd see Earth as it was 2.5 million years ago, in the Pliocene, with no humans, cities, or technology. We'd be invisible to them across the time gap created by distance and light speed. This creates a strange situation. We and hypothetical Andromedans exist simultaneously in cosmic time, but we can never see each other's present. We're separated by a temporal gap, always viewing each other's past, with no way to bridge that delay except by waiting. Andromeda is actually moving toward us. In about 4 to 5 billion years, the Milky Way and Andromeda will collide and merge, forming a new elliptical galaxy. But even this collision will happen slowly from our perspective, taking millions of years to complete. The time delay from Andromeda demonstrates that simultaneity is relative and limited. There's no universal now that encompasses both galaxies. The present is local, confined to your immediate vicinity. Beyond that, you can only observe the past, with the depth of past proportional to distance. Looking at Andromeda is genuine time travel to the past, observing ancient light carrying information about an era before modern humans existed. Fact 80. Gravitational time. Dilation means time runs slower near massive objects. Gravity doesn't just pull on matter and energy, it pulls on time itself. The stronger the gravitational field, the slower time passes. This gravitational time dilation is a prediction of general relativity, confirmed by countless experiments. Near Earth's surface, the effect is tiny but measurable with atomic clocks. Time runs about 1 billionth slower at sea level than on a mountaintop. GPS satellites must account for this, along with velocity time dilation to maintain accuracy. Near more massive objects, the effect becomes dramatic. On a neutron star's surface, where gravity is billions of times stronger than Earth's, time runs significantly slower than in empty space. If you could somehow survive standing on a neutron star, the universe around you would appear accelerated. Near a black hole's event horizon, time dilation becomes extreme. To a distant observer, someone falling toward a black hole appears to slow down, freeze, and fade, never quite crossing the horizon. But from the falling person's perspective, time flows normally, and they cross in finite time. This creates weird scenarios. If you orbited close to a black hole for what felt like hours, then returned to distant space, decades or centuries might have passed. You'd have time traveled into the future by descending into a deep gravitational well and climbing back out. Gravitational time dilation shows that time isn't absolute or universal. It's relative to your position in gravitational fields. Someone living on a massive planet ages slower than someone in empty space. The universe doesn't have one clock, but countless clocks running at different rates based on local gravity. This is real, measured, proven time travel into the future. Gravity provides a mechanism for forward time travel, limited only by your ability to survive intense gravitational fields and return to tell about it. Fact 81. A clock on a neutron star would tick measurably. Slower neutron stars are among the most extreme objects in the universe. When massive stars explode as supernovae, their cores collapse into spheres typically about 20 kilometers across, but containing more mass than the Sun. Gravity becomes incredibly intense. If you could place an atomic clock on a neutron star's surface and compare it to one in empty space, the neutron star clock would tick measurably slower. Depending on the specific neutron star, time might run at 70 to 90% the rate of distant clocks. The effect is enormous by relativistic standards. This isn't just theoretical. We observe neutron stars indirectly through their effects. Pulsars, rotating neutron stars emitting beams of radiation, allow precise timing measurements. The physics of these objects confirms extreme gravitational time dilation is occurring. If you could somehow survive on a neutron star for what you experience as 1 year, much more time would pass in the distant universe. Depending on the star's mass and radius, perhaps 1.3 to 1.5 years would pass elsewhere. You'd be effectively time traveling into the future at an accelerated rate. The problem is survivability. Neutron star gravity would crush anything made of atoms. The tidal forces would tear apart any structure larger than atomic scale. The magnetic fields and radiation would be lethal. Visiting a neutron star is impossible with any conceivable technology. But neutron stars prove that extreme time dilation isn't just mathematical abstraction. These objects exist throughout the universe, warping time dramatically. They're natural laboratories demonstrating general relativity's predictions in the most extreme conditions. They remind us that time is flexible, that the universe contains regions where time runs at vastly different rates. The cosmos is temporally diverse, with different regions experiencing different temporal flows based on local conditions. Fact 82. Cosmic rays experience almost no time due to traveling. Near light speed, cosmic rays are high-energy particles, mostly protons, traveling through space at speeds approaching light speed. From Earth's reference frame, cosmic rays might take thousands of years to cross the galaxy. But from the particle's perspective, almost no time passes. At 99.99% of light speed, time dilation becomes extreme. Time for the particle runs at about 1% normal speed. A journey that takes 10,000 years externally takes about 100 years from the particle's perspective. At even higher speeds, closer to light speed, the effect becomes more dramatic. At 99.9999% of light speed, time runs at about 0.01% normal speed. A journey of 1,000,000 years takes about 100 years subjectively. The most extreme cosmic rays travel even faster. For them, crossing the entire observable universe might occur in subjective seconds or minutes. They're born, travel billions of light years, and are destroyed, all within a subjective instant. From the particle's perspective, space itself is compressed. Length contraction, the flip side of time dilation, makes distances shrink along the direction of motion. A light year might compress to light days or light hours. The universe becomes smaller as you approach light speed. This shows that reality is relative. There's no absolute truth about how long journeys take or how large space is. It depends on your reference frame. For particles moving at near light speed, the universe is tiny and time barely passes. Cosmic rays are natural time travelers, experiencing minimal personal time. while traversing vast cosmic distances. They demonstrate that time travel into the future becomes more extreme as you approach light speed, ultimately approaching instantaneous travel through billions of years of external time. Fact 83. The universe has no universal now. Common sense suggests there's a universal present moment, a single now that exists everywhere simultaneously. But Einstein's relativity revealed something profound. Simultaneity is relative. There's no universal now. Different observers disagree about what's happening at the same time. Imagine two events occurring far apart in space. Whether they happen simultaneously or one happens before the other depends on your motion. One observer moving at high speed might see event A before event B. Another observer, moving differently, might see B before A. A third, stationary between them, might see them simultaneously. All three perspectives are equally valid. There's no absolute truth about which event happened first. Time ordering of spatially separated events isn't fixed, but depends on reference frame. This only applies to events that can't influence each other, too far apart for light to travel between them during the interval. This means the universe doesn't have a single present moment. Your now is a slice through space-time, but someone moving relative to you has a different slice, a different now. Your present includes events they consider past or future. Looking at distant objects makes this concrete. When you observe a distant galaxy, you're seeing its past. But from their perspective, observing you, they're seeing your past. Neither perspective is more correct. Both are true from their respective frames. This has profound implications. The universe doesn't exist moment by moment, but as a four-dimensional space-time where past, present, and future all exist together. The flow of time is a feature of consciousness moving through space-time, not a feature of space-time itself. Without universal now, time travel paradoxes become even stranger. If simultaneity is relative, the same time in different places becomes ambiguous. The present is local, personal, relative to your motion and position, making time more fluid and complex than everyday experience suggests. Fact 84. Light from distant galaxies shows us the early universe's conditions. The most distant galaxies we can observe appear as they were over 13 billion years ago, less than a billion years after the Big Bang. Their light has been traveling across space all that time, showing us the universe in its youth. These early galaxies look different from modern ones. They're smaller, more irregular, actively forming stars at prodigious rates. The universe was denser then, with galaxies closer together, colliding and merging more frequently. Elements heavier than hydrogen and helium were rare, as early stars hadn't yet forged and distributed them. By studying light from different distances, astronomers watch cosmic evolution. Nearby galaxies show the recent universe. Progressively distant ones show progressively earlier eras. It's like having a time machine, observing different ages by looking at different distances. The most distant individual objects detected are galaxies whose light was emitted just a few 100 million years after the Big Bang. These are among the first galaxies, made of first-generation stars, showing the universe emerging from the dark ages after recombination. The James Webb Space Telescope and other advanced instruments push this boundary, finding ever more distant, and thus earlier, objects. Each discovery extends our view deeper into cosmic time, closer to the beginning. This light carries information about conditions in the early universe: temperature, density, composition, expansion rate. By analyzing spectra, astronomers determine what these ancient galaxies were made of, how fast they were moving, what their environments were like. The ability to observe cosmic history spread across space is unique to astronomy. No other science can directly observe its subject at different ages simultaneously. The universe's vast size and light speed's finite nature create a natural time machine, letting us witness cosmic evolution from youth to maturity across billions of years. Fact 85. We can never see the present moment of distant objects due to light's finite speed. You can never see a distant object as it exists now. You can only see its past. The farther away something is, the older the image you receive. For extremely distant objects, the delay is billions of years. This creates a fundamental limitation. You can observe the past, but never the present of distant things. If you want to know what's happening on a star 10 light years away right now, you must wait 10 years for the light from that moment to arrive. There's no way around this limit. Even nearby objects have delays. The moon's light takes about 1.3 seconds to reach Earth. You see the moon as it was slightly over a second ago. The sun's light takes about 8 minutes. During a solar eclipse, the sun has already been eclipsed for 8 minutes before you see it. For conversations with astronauts on Mars, signals take between 4 and 24 minutes each way, depending on planetary positions. A round-trip communication takes 8 to 48 minutes. Real-time conversations become impossible. Every exchange involves waiting for the signal to travel across space. This fundamental light speed delay means the universe you observe isn't the universe as it exists now. It's a patchwork of different times, with each object appearing as it was when its light left. Your observable universe is composed entirely of the past, arranged by distance. If there were a hypothetical way to see distant objects present, it would violate causality. Information couldn't travel faster than light without creating paradoxes. The light speed limit protects causality, ensuring effects follow causes, but at the cost of making distant presence forever unobservable. We're isolated in time as well as space, forever viewing the past of everything beyond our immediate vicinity, with no access to the cosmic present moment elsewhere. The universe shows us only its history, never its current state. Fact 86. Black hole event horizons represent a point of no return in space-time. The event horizon of a black hole is a boundary in space-time with a unique property. Nothing that crosses it can ever return. It's not a physical surface, but a mathematical boundary, the point where escape velocity equals light speed. Once crossed, even light cannot escape. From outside, the event horizon appears frozen in time. Objects falling toward it seem to slow down, getting dimmer and redder, never quite crossing. But this is an illusion of extreme time dilation. From the falling object's perspective, time flows normally, and they cross the horizon in finite time. Once inside the event horizon, space-time warps so extremely that all paths lead inward toward the singularity. There's no trajectory, no amount of thrust that leads back out. Not because the pull is too strong, but because every direction you can move points toward the center. The future direction in space-time has become the inward direction in space. This makes the event horizon the ultimate point of no return, a one-way membrane in space-time. Information and matter can fall in, but never emerge. Classically, black holes are perfect traps, eternally growing as they consume matter and light. Quantum mechanics complicates this picture. Stephen Hawking showed that black holes slowly evaporate through quantum effects at the horizon, emitting Hawking radiation. Over incomprehensibly long timescales, black holes eventually disappear, though the information paradox, whether information is destroyed or preserved, remains unsolved. Event horizons demonstrate extreme space-time curvature. They're boundaries where time and space exchange roles, where causality becomes directional in space rather than time, where the structure of space-time itself forbids certain possibilities absolutely. They're natural laboratories for studying extreme physics, where general relativity, quantum mechanics, and thermodynamics meet in mysterious ways. Event horizons represent the universe at its most exotic, showing what happens when gravity warps space-time to its limits. Fact 87. Gravitational waves carry information about space-time itself. Gravitational waves are ripples in space-time itself, traveling at light speed, carrying information about violent cosmic events. When massive objects like black holes or neutron stars collide, they shake space-time, creating waves that propagate outward like ripples on a pond. First predicted by Einstein in 1916, gravitational waves weren't directly detected until 2015. when LIGO observed waves from two colliding black holes over 1 billion light-years away. This detection opened a new window on the universe: gravitational astronomy. Unlike light, which is absorbed or scattered by matter, gravitational waves pass through everything almost unimpeded. They carry pristine information from their sources, allowing us to observe events invisible to telescopes. We can see black hole collisions, neutron star mergers, and potentially even echoes from the Big Bang itself. Gravitational waves don't carry information about objects moving through space-time. They are information about space-time's dynamics. When a wave passes, space-time itself stretches and compresses rhythmically. Distances between free-floating objects oscillate slightly as the wave passes through. Detecting them requires incredible precision. LIGO detects changes in distance smaller than a proton's width across kilometers of space. The technology is at the edge of what's physically possible, measuring space-time's subtle oscillations against overwhelming backgrounds of noise. Gravitational waves travel at light speed, so they show us the past, like light does. Waves detected on Earth began their journey millions or billions of years ago, carrying news of ancient cosmic collisions across space and time. They represent a fundamental prediction of general relativity. Space-time is dynamic, not static. It can wave, vibrate, and carry energy. Understanding gravitational waves deepens our comprehension of space-time's nature and gives us tools to explore the universe's most energetic events. Fact 88. The cosmic microwave background is light from 380,000 years after the Big Bang. The cosmic microwave background, or CMB, is the oldest light we can observe, released when the universe was just 380,000 years old. Before this time, the universe was opaque, filled with hot plasma that scattered light. When it cooled enough for atoms to form, light could travel freely for the first time. This moment, called recombination, released light that's been traveling through space ever since. Stretched by cosmic expansion from visible light to microwaves, it fills the entire sky uniformly, coming from every direction. When you tune a radio to static, a tiny fraction of that noise is actually ancient CMB photons. The CMB shows the universe when it was much simpler and more uniform than today. Tiny fluctuations in temperature, about 1 part in 100,000, represent the seeds that grew into galaxies, stars, and clusters. These fluctuations are the baby picture of cosmic structure. By studying the CMB's properties, its temperature, spectrum, and patterns, cosmologists determine the universe's age, composition, geometry, and history. The CMB encodes vast information about cosmic conditions 13.8 billion years ago, decoded through careful observation and analysis. This radiation is the ultimate look into the past. We're seeing the universe in its infancy, less than 1,000th of its current age. The CMB is direct observation of the early universe, preserved across cosmic time and space. Every direction you look, you see this ancient light, always at the same distance, creating a sphere around Earth called the surface of last scattering. It's the farthest we can see with electromagnetic radiation. Earlier times are hidden behind the opaque plasma wall. The CMB is like a time capsule, information preserved from near time's beginning, waiting billions of years to be decoded. It's evidence of the universe's history, confirmation of Big Bang theory, and a window into conditions when everything was hot, dense, and simple. Fact 89. Time began at the Big Bang current. Physics suggests time itself began with the Big Bang about 13.8 billion years ago. Before the Big Bang, there was no before. Time didn't exist. The question, what happened before the Big Bang, might be meaningless, like asking what's north of the North Pole. This is a strange concept. We're used to thinking every moment has a previous moment. Every event has prior causes. But if time began at the Big Bang, the first moment has no predecessor. Time's arrow points forward from the Big Bang, but there's nothing behind it. General relativity suggests the Big Bang was a singularity, a point where space-time curvature becomes infinite and physics breaks down. At this singularity, our equations fail. We can't describe what happened at the Big Bang because time itself was ill-defined. Some theories propose alternatives. Perhaps time existed before the Big Bang in some form. Maybe our universe emerged from a prior universe, or the Big Bang was a transition rather than an absolute beginning. Quantum cosmology explores scenarios where time behaves strangely near the origin. The Big Bang as time's beginning implies the universe is finite in age, but potentially infinite in extent. Time has a start, but space might stretch infinitely. Or perhaps both time and space are finite but unbounded, like the surface of a sphere. If time began at the Big Bang, the universe's age is absolute. 13.8 billion years is all the time that's ever existed. Everything that ever happened fits within this span. Before this, there was nothing. No events, no duration, no existence. This beginning of time shapes everything. It's why the universe has an age, why we can see only so far, why there's a horizon to the observable universe. Time's origin defines cosmic history's starting point, the moment when everything began. Fact 90. The universe's expansion affects how we measure cosmic time. The universe is expanding, with galaxies moving apart as space itself stretches. This expansion affects how we measure time and distance across cosmic scales. Distant galaxies aren't just far away. They're far away in an expanding space, complicating measurements. When we observe a galaxy 1 billion light-years away, we're seeing light that left when the universe was smaller and younger. The galaxy has since moved farther due to expansion. Its current distance is greater than 1 billion light-years, perhaps 1.1 or 1.2 billion, depending on expansion rate. This expansion means cosmic time and distance are intertwined in complex ways. Cosmologists use various distance definitions: proper distance, how far apart objects are now; co-moving distance, which factors out expansion; light travel distance, how long light traveled to reach us. The expansion also redshifts light, stretching wavelengths as space expands. The amount of redshift tells us about expansion history, allowing astronomers to measure distances and determine when light was emitted. Redshift becomes a kind of cosmic clock. For the most distant objects, expansion becomes extreme. Galaxies at the edge of the observable universe are receding faster than light, not through local motion, but through space expansion between us and them. We can still see them because their light was emitted when they were closer. The expansion rate itself changes over time, first decelerating due to gravity, then accelerating due to dark energy. This changing expansion complicates cosmic time measurement. There's no single simple relationship between distance and time across cosmic history. Understanding cosmic expansion is essential for interpreting astronomical observations. Every measurement of distant objects involves correcting for expansion, understanding how space has stretched since light began its journey. Time and space expansion are fundamentally connected in cosmology. Fact 91. Quantum computers might simulate time travel scenarios. Quantum computers, using quantum mechanical principles like superposition and entanglement, might enable simulating complex time travel scenarios that classical computers cannot. They could model closed time-like curves, explore paradox resolution, or simulate quantum systems with retrocausal effects. Time travel involves intricate causality loops and consistency requirements that are computationally intensive to model. Classical computers struggle with the exponential complexity. Quantum computers, naturally handling superposition, might simulate all possible self-consistent timelines simultaneously. Researchers have already used quantum systems to simulate simplified closed time-like curves, studying how quantum mechanics might handle paradoxes. These experiments suggest quantum effects naturally enforce consistency, preventing logical contradictions through interference and measurement effects. Quantum computers might also simulate the quantum field theory near black holes, wormholes, or other exotic space-time structures where time behaves strangely. Understanding these extreme conditions could reveal whether time machines are physically possible and how they'd behave. Additionally, quantum computers might exhibit strange temporal effects themselves. Some quantum algorithms seem to reach backward in time computationally, accessing information about future possibilities in ways classical algorithms cannot. This isn't time travel, but shows quantum computation has unique temporal properties. If time travel involves quantum mechanical effects, as some theories suggest, quantum computers become essential research tools. They're the only way to accurately simulate quantum systems complex enough to exhibit interesting temporal behavior. Quantum computers won't enable actual time travel, but they might help us understand whether it's possible, how it would work, and what limits nature imposes. They're tools for exploring time's quantum nature, probing the boundaries between the possible and impossible at the intersection of quantum mechanics and relativity. Fact 92. Cryogenic freezing is a form of one-way time travel. Cryogenic preservation, freezing bodies or brains at death in hopes of future revival, is essentially one-way time travel to the future. You're preserved in the present, skip forward through time while frozen, and might be revived in a future with advanced medical technology. The concept is that if preservation is sufficiently good, future medicine might repair damage, cure diseases, and restore life. You'd effectively have traveled decades or centuries forward, waking in a world radically different from the one you left. Legally, cryonically preserved people are dead. The procedure happens after legal death, preserving the body before information encoded in brain structure degrades. Whether this preserves identity, consciousness, or personhood is unknown and controversial. Current cryonics faces enormous challenges. Freezing causes ice crystal damage. Existing techniques use cryoprotectants to reduce this, but preservation quality is uncertain. We don't know if current methods preserve enough brain structure to enable future revival. It's a gamble on future technology. Revival would require technology that doesn't exist and might never exist. Cell-by-cell repair, reversing freezing damage, curing the original cause of death, and somehow restarting consciousness. These are massive, possibly insurmountable challenges. Still, some people choose cryonic preservation, viewing it as better than certain death. Even a small chance of future life seems preferable to none. It's a belief in future progress that coming centuries might solve problems we can't today. Cryonics represents a practical, though speculative, form of time travel. Rather than moving through space-time at high speeds or through wormholes, you preserve your physical structure across time, hoping future technology can restore function. It's time travel through patience and technology, skipping forward while frozen until conditions improve. Fact 93. Generation ships traveling to distant stars would experience time dilation. Generation ships are hypothetical spacecraft traveling to distant stars over centuries or millennia, with multiple generations living and dying during the journey. Even without approaching light speed, these journeys involve time, though time dilation effects would be small at achievable speeds. If we developed propulsion allowing travel at 10 or 20% of light speed, time dilation becomes noticeable. At 10% light speed, time runs at about 99.5% normal speed. Over a century-long journey, travelers age about 6 months less than Earthbound people. At higher speeds, effects increase. At 50% light speed, time runs at about 87% normal rate. A generation ship traveling for 100 Earth years would experience about 87 years subjectively. The crew ages slower than people back home. This creates interesting scenarios. Travelers leave Earth, spend decades or centuries aboard ship, and arrive at their destination to find Earth has aged more than they have. If they maintained communication, they'd watch Earth accelerate through time relative to their slower experience. For truly long journeys at modest speeds, psychological and social time becomes as important as relativistic time. Generations born aboard ship would have different perspective on time than the first generation. The journey becomes their entire known existence, a mobile world traveling between stars. Even without extreme time dilation, these journeys represent temporal displacement. Travelers leave one era and arrive centuries later, finding both their destination and Earth radically changed. They're time travelers by virtue of long journey, skipping through time while alive but isolated. Generation ships highlight that time travel doesn't require exotic physics. Simple motion through space at high speeds, given enough time and distance, creates temporal displacement. The traveler's timeline and Earth's timeline diverge, running parallel but at different rates. Fact 94. Digital immortality could preserve consciousness for future revival. Digital immortality proposals suggest uploading consciousness to computers, creating digital copies that could exist indefinitely, pausing and restarting at will. This would enable a form of time travel, where digital minds skip forward through time between active periods. If consciousness could be digitized, the digital copy could be frozen like a computer file, preserving its exact state indefinitely. Centuries could pass externally, while the digital mind remains unchanged. Upon reactivation, it would experience jumping forward through time, the ultimate form of cryonic preservation. This assumes consciousness is purely information, that mental states can be captured computationally. This is philosophically controversial. Does copying brain structure copy consciousness, or just create a similar but distinct consciousness? Would the digital copy be you, or a different entity that merely thinks it's you? Technical challenges are immense. Mapping every neuron and synapse, understanding how brain structure encodes consciousness, creating computers that can run these simulations at adequate speed, all remain distant goals. We're nowhere close to uploading consciousness. Even if possible, digital immortality raises questions. What does existence mean for a digital mind? What experiences would it have? Could it be copied infinitely? Would the copies be the same person or different? Questions about identity, continuity, and personhood multiply in the digital realm. Still, some researchers pursue this seriously, viewing it as eventual technology. If achieved, it would enable unprecedented time travel. Digital minds could hibernate for centuries, waking occasionally to experience different eras, gathering knowledge across vast time spans. Digital immortality represents another speculative form of time travel, using computation rather than space-time manipulation. Whether consciousness can be digitized remains unknown, but if possible, it would fundamentally change our relationship with time, making centuries pass like sleep between periods of wakefulness. Fact 95. Faster space travel would require accounting for time, dilation effects. As humanity develops faster spacecraft, time dilation becomes increasingly important. Even at modest relativistic speeds, time differences accumulate. Mission planning would need to account for how much less time passes for travelers than Earthbound people. At 30% light speed, achievable with advanced fusion or antimatter propulsion, time runs at about 95% normal rate. A 10-year round trip to a nearby star would take about 10 years Earth time, but only 9.5 years traveler time. The difference is small but measurable. At 70% light speed, time runs at about 71% normal rate. A 10-year round trip. Earth time takes only 7.1 years for travelers. They age 3 years less than people who stayed home. This creates practical concerns about synchronizing activities across different reference frames. For missions to distant stars at high speeds, time dilation becomes dramatic. Travelers might spend decades subjectively while centuries pass on Earth. They'd return to find everyone they knew dead, civilization transformed, technology advanced. They're time travelers whether they plan to be or not. This affects mission planning. Do we send astronauts knowing they'll be temporarily displaced? How do we handle the psychological impact of time travel? Crew members would effectively emigrate not just to space, but to the future. Space agencies would need to develop protocols for managing time dilation, maintaining synchronized activities between Earth and fast-moving spacecraft, accounting for aging differences, planning for travelers returning to a different era than they left. Time dilation isn't a problem to be solved, but a feature of reality to be accommodated. Fast space travel inherently involves time travel. Any civilization exploring the galaxy will become time travelers, spreading not just through space, but through time as well. Fact 96. Future civilizations might possess technology to manipulate space-time. While current technology can't create wormholes or warp drives, future civilizations, perhaps thousands or millions of years more advanced, might develop capabilities that seem impossible today. Advanced technology could potentially manipulate space-time, enabling time travel. Consider how much human technology has advanced in just a few centuries. From wooden ships to spacecraft, from abacuses to quantum computers, our capabilities have grown exponentially. Extrapolate this forward millennia, and the technologies become unimaginable. A sufficiently advanced civilization might generate or collect exotic matter, stabilize wormholes, create microscopic black holes and manipulate them, harness energy from stars, or even matter-antimatter annihilation on massive scales. They might understand physics beyond our current theories, discovering principles we haven't glimpsed. If time travel is physically possible but technologically difficult, it might be within reach of far future civilizations. They might visit the past or future, explore alternate timelines, or manipulate causality in ways we can't conceive. This raises questions about why we don't see time travelers from the future. Perhaps time travel is impossible after all. Or perhaps future civilizations exist, but choose not to visit our time. Or maybe they visit, but remain undetected. Or perhaps paradoxes and consistency requirements prevent interference with the past. The absence of obvious time travelers might mean time travel remains impossible regardless of technology. Or it might mean we're early in the universe's history, before civilizations advanced enough to develop time machines emerge. Future technology represents unknown possibilities. Whether time travel is achievable depends on physics we don't fully understand. Advanced civilizations might crack problems that currently seem insurmountable, opening doors we can't yet imagine. Time travel might await discovery by beings far more advanced than us. Fact 97. Particle accelerators create conditions. Where time behaves strangely, particle accelerators like the Large Hadron Collider accelerate particles to 99.9999% of light speed or higher, creating extreme time dilation in laboratories. These particles experience time much slower than stationary observers, living longer than their normal lifetimes. Unstable particles that normally decay in microseconds can persist for milliseconds or longer when accelerated to near light speed. This allows physicists to study them in detail despite their brief lifetimes. Time dilation is essential for particle physics research. These accelerators also recreate conditions from the early universe, when everything was hot, dense, and energetic. Particle collisions produce exotic states of matter that haven't existed since shortly after the Big Bang. In a sense, accelerators are time machines, bringing ancient cosmic conditions into the present. The energies and conditions in these experiments involve regimes where quantum mechanics and relativity both matter. Particles exhibit quantum behavior while moving at relativistic speeds, creating situations where time becomes quantum mechanical, fuzzy, and strange. Some experiments show particles seemingly affecting their past states, quantum interference across time, and other effects suggesting time's nature is more complex at quantum scales than classical physics suggests. Particle accelerators push physics to extremes, revealing how time behaves under unusual conditions. They're laboratories for studying time itself, exploring its quantum nature and relativistic properties simultaneously. While these experiments don't enable human time travel, they demonstrate that time is far stranger than everyday experience suggests. Understanding how time behaves for accelerated particles might eventually reveal principles relevant to macroscopic time travel, or might confirm fundamental limits preventing it. Accelerators show that time travel of a sort happens constantly in laboratories worldwide. Subatomic particles routinely experience time differently than we do, traveling into our future while barely aging themselves, demonstrating that time's flexibility is real and measurable even in routine physics experiments. Fact 98. Quantum experiments have shown particles seemingly violating causality. Certain quantum experiments produce results that seem to violate normal causality, with future measurements appearing to affect past states. The delayed choice quantum eraser is the most famous example, showing how observation choices made after a photon has passed through apparatus can affect results in ways that seem retrocausal. In these experiments, a photon's behavior at an earlier time seems determined by measurements made at a later time. It's as if information travels backward from future to past, though careful analysis shows information isn't actually transmitted, so causality isn't truly violated. These experiments reveal that quantum mechanics and time have a strange relationship. The past isn't fixed at the quantum level until observed. Quantum states exist in superposition, and measurement chooses which past actually occurred from among multiple possible pasts. This doesn't allow sending messages to the past or creating paradoxes. The effects are statistical, visible only when comparing large numbers of quantum events. Individual outcomes remain random, preserving causality while allowing strange correlations across time. Some physicists interpret these results as evidence that quantum mechanics involves retrocausality, genuine influence from future to past at microscopic scales. Others argue it's an artifact of how we describe quantum measurement, not real backward causation. These experiments suggest that at quantum scales, the distinction between past and future might be less absolute than at macroscopic scales. Time might be fundamentally different in the quantum realm, more symmetric, more flexible, allowing connections across time that classical physics forbids. Understanding quantum time effects might be crucial for unifying quantum mechanics and relativity. The intersection of quantum mechanics, gravity, and time remains mysterious, possibly hiding principles that would explain whether time travel is ultimately possible or impossible at fundamental levels. Fact 99. Information could theoretically be sent backward in time on quantum scales. While macroscopic time travel faces enormous obstacles, some theories suggest information might be sendable backward in time on quantum scales. This wouldn't enable human time travel, but could have profound implications for physics and computation. Certain interpretations of quantum mechanics allow retrocausal effects, where future measurements influence past quantum states. If controllable, this might enable sending information backward, though likely only at microscopic scales and over tiny time intervals. Quantum computers might exploit retrocausal effects if they exist. Some proposed quantum algorithms seem to involve reaching backward in time computationally, though whether this represents genuine retrocausality or just unusual computational flow is debated. The problem is control. Even if quantum mechanics allows retrocausal influence, harnessing it to send specific information remains unclear. Random quantum effects don't constitute communication. You'd need to control and encode information in backward-traveling quantum states. If information could be sent to the past even microscopically, it would revolutionize physics. It would enable bypassing computational limits, solving problems by sending solutions to yourself from the future. It might also create paradoxes, requiring new understanding of causality and consistency. Most physicists are skeptical that controllable backward time information transfer is possible. Quantum mechanics is carefully balanced to allow strange correlations while preventing paradoxes and faster-than-light communication. Retrocausality might be another correlation that can't actually transmit information. Still, the theoretical possibility exists in some formulations. Future developments in quantum mechanics and gravity might reveal mechanisms for backward information transfer, or might prove it's fundamentally impossible. The question remains open, representing the frontier where quantum mechanics, relativity, and time mysteries meet. Fact 100. The future isn't written yet. We've explored time travel through physics, paradoxes, perception, and possibility. But here's perhaps the most important fact. Quantum mechanics suggests reality is probabilistic, meaning the future isn't predetermined. Multiple possible futures exist simultaneously until choices and quantum events collapse possibilities into actuality. Unlike the past, which is fixed in space-time, the future remains open. Your choices matter. Quantum uncertainty means even identical initial conditions can lead to different outcomes. The universe isn't a deterministic machine running predetermined code, but a probability cloud of potential futures constantly collapsing into actual presents. This has profound implications for time travel. If the future doesn't exist yet, how could you visit it? You'd be visiting a future that's only one of many possibilities, perhaps creating or selecting that particular timeline by visiting it. Time travel to the future might be self-fulfilling, making one possible future real by observing it. Quantum indeterminacy also provides a mechanism for resolving paradoxes. If you travel to the past and try to change things, quantum effects might ensure only self-consistent outcomes actually occur. Paradoxical timelines have zero probability. Nature uses quantum mechanics to enforce chronology protection. This means your life isn't predetermined. Time travel or not, you're creating the future through your choices. Each decision point represents quantum collapse, selecting one branch of possibility over others. You're navigating through possibility space, creating history as you go. The future's openness is hopeful. It means change is possible, that tomorrow isn't locked in, that consciousness and choice matter. You're not a passive observer of predetermined events, but an active participant in creating what comes next. As you drift off to sleep tonight, remember, you're traveling through time right now, moving from past through present toward an undetermined future. You're a time traveler, experiencing the grand mystery of temporal flow, participating in the universe's unfolding. Tomorrow awaits, unwritten, full of possibility. Sweet dreams, time traveler.